Hi, jury members. I'm so excited to have you meet the teams today. This can be a long day for all of us, especially when we are online. I will need to interrupt people, including you, from time to time to help us stay on time. Please don't mind. I'm looking for your support for this. Please keep your comments and questions short and to the point. Okay, we are going live. Hello, everyone. Welcome to the Education Division. My name is Garima Kamra, and I am the jury coordinator of this division. It's my job to keep us on time, and I'll be taking this very seriously. Our finalist teams have put in a lot of hard work. They submitted their project reports about a month ago, and today these teams will present their work to the jury. The Education Division has three jury members with expertise in net zero and resilient buildings. We have Aarti Nayan. Aarti is an energy efficiency policy specialist with expertise in net zero energy buildings, sustainable cooling, financing, and utility scale programs. She advises think tanks, government agencies, and private sector companies on energy efficiency. Hello, Aarti. Next, we have Shriti Pandey. Shriti is founder of Straw Structure Eco that makes compressed agri fiber panels, which is 100% green building material. Her initiative stops crop stubble burning, which is the leading cause of air pollution in northern India. Our third jury member is Harsh Thapar. Harsh is the founder of Envirolizer. Harsh has delivered on prominent high performance projects like the Mazda City, Abu Dhabi, New Apple Campus, San Jose, which is a LEED Platinum building, Bloomberg Headquarters Office, London, which is a BREEAM Outstanding building, and Amravati New Building Complex, New Capital Complex in Andhra Pradesh, India. Hello, Harsh.
Hi.
These jury members, yeah, hi. These jury members have had over 2 weeks to review the reports submitted by the teams. They have looked at your work in detail and have already assessed your entries for the 10 contests of the decathlon. Students, your presentations will help them hear your narrative. They will assess your presentations and your mastery over the solution through the Q&A session. They may revise their scores based on what they hear from you today. Our first presentation is from Team Abhijan. They have worked on Swami Vivekanand High School and Junior College in Bangalore. Their project partner is Vivekanand Education Society's College of Architecture. Let's do a quick AV check for our presenters. Hi Ritika, can you say something?
Hi.
Yeah, good.
Hello, I am Ritika
Hi
Lal.
Amrita. Yeah, hi Ritika. Hi Amrita, can you unmute yourself and say something? Yeah, hi, good. Hi Nishant.
Hi, ma'am.
Hi Anjali.
Hi, ma'am.
Okay. So, have you shared your presentation? Please share the presentation.
Yes, I will share it.
Yeah.
Should I start?
I cannot see your presentation yet. Share your screen.
I have here. Share. Now is the presentation visible?
No, sorry, cannot see your presentation.
Just give me 1 minute.
Sure.
Visible?
To the presentation mode, please.
Slideshow mode.
It's not in slideshow mode yet.
Now,
It's not in slideshow mode yet. Please put in
this is
slideshow mode. Yeah, go to page 1, slide 1. This is your first slide. Okay. Okay, so team, you will be having 25 minutes to present your work to the jury. At 20 minutes, I will ring a signal which would sound like this. You won't have a 26th minute, which means at 25 minutes,
okay.
I will stop you and ask you to end your presentation. After that, we will have 15 minutes for a Q&A session. Please
Okay.
keep your answers direct and to the point. Your project partner may also provide some comments. Okay, team, if you're not speaking, you can keep yourselves at mute and the stage is yours. Well, all the best.
Thank you. So, good morning, everyone. This is Team Abhijan presenting about net positive VS School and Junior College. The team was divided by two faculty advisors and one faculty lead. We are a multidisciplinary team architects and instrumentation engineering this ideology in the school of the six parameters addressing the society.
Goal set by the team was to achieve EPI of 20 kilowatt hour per square meter per year, to recycle 100% of wastewater and harvest 100% runoff on site, utilization of fast construction technology. Yeah, just a second. To recycle 100% of wastewater and harvest 100% runoff on site, utilization of fast construction technology to save time and encourage the use of recycled products. Biophilic design is adopted to improve physical and mental well-being of users and to reduce PM 2.5 from 187 AQI to 20 AQI to achieve maximum thermal comfort hours. To make a contextual design and enhance community participation, to create structural modularity for making multi-usable spaces. Resilience is to be achieved for flood, increasing air pollution, and pandemic situations to provide sensory playscapes for students.
So the site is located in a developing urban suburb of Mumbai Chembur. As shown in the map, it is seen that it is surrounded by a densely populated surrounding and a settlement. So the site area is 2650 square meter with an FSI of 2. So this is the development plan of Mumbai 2034, which states that there is a 36-meter highway which is coming near the site. So according to that, there will be a boom in the construction industry. So according to 99acres.com, there are 727 new and in-process building construction in Chembur. So there will be a rise in the use of the materials. So these are some local materials used in construction in Mumbai. So how can we as a team mitigate the effects of this material on the surrounding? So as you can see, this is the site, and near the site, there is a Trombay refinery. So according to the graph, it is shown that there is PM 2.5 particulate matter, which is very high in this region. So which causes the diseases which are mentioned in the graph below. So according to the contour map, the site is 2 meters above sea level, and it forms a saucer zone in this region, which causes a natural flow of drainage in the site. Also, as you can see, there is a stormwater drain system, but when we visited the site, there was a lot of waste which was gathered near it, which causes more water logging and causes the site to be flooded.
The team conducted shadow analysis of surrounding build form on site for 21st June and 21st December. It was concluded that approximately 36% of the time site is shaded throughout the year. There There is a convenient accessibility of public transport and hospital facilities for the users to access within a range of 500 meters. The site is covered by existing fully grown trees and shrubs, so the team decided to retain them during the construction and completion of the project. The site is surrounded by 9-meter wide road on three sides, that is north, south and east, and residential building on west, east and north, and an educational building on the southern side. The The team conducted sun path analysis of site. The sun travels north during June, July, and August, which receives more diffuse light than direct solar radiation due to more cloud cover on uh, the west, east, and the southern facades are the more critical facade. So the build form is designed north-south elongated, with the west facade having minimum surface area. The design has a self-shaded courtyard, and the shadow analysis conducted shows how it reduces the heat gain. According to the windrow's analysis, primary wind direction is west. So, having an open courtyard and forming a C-shaped build form allowed the form to play with negative and positive wind pressure, which will enhance the cross ventilation strategy. The wind has more humidity in June, July, and August and September, and more heat from October to April. The average wind velocity is 1 meter per second.
For climate analysis, the graphs were divided into two parts. In this dry bulb temperature graph, it was observed that from March to October, dry bulb temperature is not in the comfort zone. In the peak month, is not in the comfort zone. In the peak month of May, temperatures are high, but during this month, the school is closed for the students. From the relative humidity graph, it was observed that between June to September, humidity reached up to 80%, and from October to May, it is approx 60%. There is a humidity in the air. As average wind speed is 1 meter per second, it will be reduced to zero point 0.5 to zero point 0.2 meter per second till it reaches the students. The build form also requires fan force ventilation. In the diurnal variation graph, from June to September, there is more diffuse light as compared to direct solar radiation, and from October to May, it is vice versa. So, solar power generated during these months can be stored and used during rainy season, which is from June to September. The bioclimatic chart concludes that natural ventilation is required throughout the year. The team has incorporated cross ventilation and passive strategies along with mechanical ventilation of closed loop water based structural cooling to achieve thermal comfort for the users.
So coming to the architectural concept, the concept of the design was to have sensory place clay. So when a user is actually approaching the structure, so it's divided into three zones. So one is an organized zone, one is disorganized, and one is a services zone, which will connect the user to the facade. When the user approaches the entrance, there are some creepers with flowers along with it, which smell. So it will actually have a smell connection. And inside, when they enter, there is a banyan tree where the users have the sitting space. So they don't crowd near the road and they actually come inside and have an interactive place to sit. So there are staircases on the opposite direction, north and south, which have small and big windows, which will create a play of light. So because of that, because of that, so the users will actually understand in which direction they are moving. So they will understand sun path. So when the user approaches the lobby area, so there are seasonal flowers along with some textured walls. So we usually have an habit of moving our hair around the walls when we are walking. So they will actually feel the texture and see in which season they are according to the flowers blooming. Also, the classroom has three levels: the window level, the level below them, where it is a dark color because they usually put their legs out there, and at the top, it is a different light shelf level for them to interact with three zones.
It is a ground plus 5-story structure. The ground floor is a non-functional space and kept semi-open for the users to interact. On the first level, there is administration, principal office, library, along with senior KG and junior KG classrooms. Keeping admin on the first floor allows the user to easily access it. Second level has a computer lab and fifth and sixth standard classroom. To increase the thermal comfort and reduce the cooling load, the administration and computer labs are kept at the lower level. The level 3 and 4 have canteens along with 7 to 10 standard classrooms. Having canteen in middle allows the student to easily access it. The last level has 11th and 12th standard classroom along with labs. The labs act as a buffer zone to the lower levels. The design has toilets on all the levels for easy access. The roof is divided into three zones, namely for the solar panels, the hydroponic, and an interactive zone along with closed water loop cool towers. The ground floor level has banyan tree which connects the user to the traditional learning, and the top level of hydroponics connects to the modern technology. 40% of open ground area is dedicated as an outdoor play area.
So it is a composite structure with oil palm lumber, cross-laminated timber walling, and RCC structural system. So there are modular furnitures designed from Tetra Pak waste, and railing are designed with foundry and plastic waste. As it was mentioned earlier, with increasing construction activities in the region, there will be a rise of increasing material. So, to reduce the CO2 emission of this material, we decided to go for cross-laminated timber panels, which is minus 0.42 CO2, which will absorb the CO2 from the surrounding. Talking about the double skin facade for daylighting. So the design has a double skin facade such that so the eye level. So if a student is sitting at 0.8 meter, so the window level he needs a visual connection to the outside. So the facade where he needs a visual connection is shorter, and where he doesn't need a visual connection is longer. So there is an alternate staggering of windows. Also, these are the waste pipes of 50 dia. So and they are coated with a reflective coating of 90%. So calculating the U value of window plus framing, it comes up to 0.16 watt per meter square. So with this arrangement of alternative windows and double skin facade, we were able to achieve 90% of useful daylight illuminance in 90% of the area. So according to ECBC, we need 60% of the area. So we are 30% more than the ECBC plus value in all the regions. So there is efficient daylight in the spaces. Also, in case of fire emergency, according to NBC 2016, we require maximum 30-meter running distance. So, in case of fire, the users will easily be able to access the circulation staircase, which is only 30-meter in their running distance. Also, as we can see vertically, they are connected one after the another, so it will be easier for the user to escape in case of emergency.
Different biophilic patterns are integrated in design to improve the health and well-being of the occupants. Green walls are integrated with the structure to create visual connect with the nature. Connection with natural system is created by using seasonal plantation in the facade, which would make us aware of the changing seasons. Material connection with nature is created by using wood as a walling material for the external and internal walls. Dynamic and diffuse light is experienced by the user while walking through the corridors and in the classrooms. Thermal variability is experienced by the user as one passes from corridor into the classroom, as there is a structural cooling system being used in the classroom which has lower temperature than outside temperature.
The team calculated daily consumption of equipment according to climate and number of days the school is functioning. Annual energy consumption was calculated, which was 75,000 kilowatt per hour per year, with an EPI of 14.46 kilowatt per hour per square meter per year. Considering the area on the roof and energy consumption, 540 watt panel was selected, so in total, 360 square meter of area will be covered using 150 panel, which will produce around 90,000 kilowatt per year energy, which makes a project net energy positive. We are generating more than consuming. So net metering is adopted in a project.
The total the water the project recycles water and harvests the rainwater, which makes it net water positive. The project has a septic tank treatment, as there will be more liquid flushing as compared to solid waste flushing in school. Primary treatment of sand filtration and secondary treatment of activated carbon is done with alum dosing to remove all the pathogens in the water and wastewater and reuse it for landscaping and flushing. The project is also harvesting rainwater of 3008 kiloliter of water, which will be used for landscaping and flushing.
We have incorporated hydroponics in our project. which is a method of soilless cultivation of plant. The type of hydroponic system used in a project is nutrient film technique, as this technique works best for plants that do not require a lot of support, are lightweighted, and grows fast so that they can be harvested quickly. In this setup, we can plant approximately 2500 to 2700 plants in one harvest. RO5 recycled water is used in this setup. Water consumed by the whole system is approximately 1000 liters, which is much less than the traditional method. By implementing hydroponic in our system, by implementing hydroponic system, we can teach a future generation about harvesting fresh and nutritious vegetables and fruits. The whole system is set up in an approximate area of 24 meters into 8 meters on the terrace, which helps us to reduce the solar heat radiation, which indeed helps us in achieving thermal comfort.
So the graph shows the average solar incident on surfaces. As you can see, in the month of March, April, May, it is higher as compared to the other months. But in these months, there are more holidays in the school. We also plotted the dry bulb temperature graph. So as we are using a closed loop water cooling system, the water which would be coming from the outlet will be 4 degrees higher than the wet bulb temperature. So this will be included in the calculation which the team conducted. So talking about the thermal comfort. So indoor thermal comfort means that the body can effortlessly remove its metabolic heat from itself and does not receive any from the outside. So if the structure is below the body temperature, which is 36 degrees Celsius, it will absorb the body heat. If it is above, it will transmit the heat to the body. So in such cases, the user will feel uncomfortable. So would it be more sensible to cool a building which is passively absorbs the body heat rather than allowing it to actually heat up and then design a cooling system which consumes more energy and money? So how can we make an affordable cooling system? So while discussing with our project partner, so the team compared a chiller-based and a closed-loop cooling tower system. So the built-up area of the entire project is approximate 55,000 square feet. So considering 300 square feet rule, like if 300 square feet requires 1 ton of air conditioning, so around 100 TR of machine will be required. So which will consume around operating cost of 175 kilowatt and 1120 kilowatt will be its daily consumption. So large area of solar panels will be required. So as we had site constraint and we had to go vertically higher, we have less roof area there. So having so many solar panels won't be convenient for us and it won't make the project net zero energy. So the team decided to go for a closed loop water cooling structural system. So in Mumbai, the surface temperature on the slab goes up to 45 degrees Celsius. So the roof will actually radiate the heat to the other structural materials and it will radiate the heat to the students. So as the students are not moving and they are static at one place, they will feel uncomfortable. So the team decided to structurally cool the entire structure with 20 pipes having a room water temperature running through them at zero point 0.8 meter per second. So this will decrease the surface temperature to 32 degrees Celsius, which is lesser than the body temperature. So we will radiate heat out to the surfaces and it will make the students comfortable. So along with it, we also need fan force ventilation as mentioned earlier. So there will be a cross ventilation system happening. So in total, for the entire project, there is 15,600 meters of pipe length will be required. So these were the calculation which the team conducted to see how much the heat will radiate by respiration, evaporation, radiation, and convection, and how much heat will be removed from the pipes.
The map shows hectares of oil palm plantation in India. There is approximately 3 lakh hectares of oil palm plantation, which will produce 1.7 crore cubic meter of oil palm wood waste. The team suggested to utilize this wood as an alternative to hardwood, as excess deforestation will result into future problem in case of hardwood for CLT. Economic lifespan of oil palm tree is 25 years, after which it becomes difficult for farmers to remove roots from trees. So the tree is poisoned and burned, which creates many environmental problems. So why not utilize this byproduct as a construction industry material? The site is small and has a narrow road surrounding it, which will create a problem for neighborhood if large trucks and cranes are utilized for the project. So the team decided to go with structural RCC and create panels of CLT which can be manually lifted. panel comprises of 5 layers of oil palm lumber with polyurethane adhesive will increase its density to 436 to 591 kg cubic meter, which is suitable for walling material. This shows how the entire process is carried out from the oil palm farms to the making of the panels.
Resilience against pandemic. Ground floor is kept as a non-functional space and used as an interactive space by the students during break time, as well as to avoid traffic on the road. It will be used as a waiting space. In case of pandemic, it can be used for other purposes as well. Furnitures are designed to be stackable, which makes it multi-usable for other purposes in case of emergency.
Resilience against flood. So the entire compound wall will be solid, as well as during. So if there is a gate, it will be actually open. So in case of gate, we have designed a flood gate, which will stop the outside water to come inside if there is flooding. Along with that, the water which is runoff on site, which also will also be stored on site. So for that, at the ground floor, we have designed two tanks. So these two tanks have a capacity of 21.6 cubic meter and 26.586 cubic meter. So these tanks are designed according to 944 per day rainfall, which is critical, which was happened on 26 July 2005. Air pollution. As mentioned earlier, there are many refineries and industries nearby this region. So the team decided to go with U-breathe products. So according to that product, so if there is PM 2.5 at the level of 220, it can reduce it to 20 within 15 minutes if one plant is planted in 200 square feet of area. So if so in the entire classroom we have four such plants. So the results of a research paper stated that leaves with a density of 85 leaves per zero point 0.4 square meter could reduce this particulate matter to 60%. So the plants of the leaves will actually slow down this particulate matter and won't allow it to pass through the green facade. So the entire project is covered with a green wall of 234 square meters.
The total project estimate is about 11 crores, which comes to 2000 rupees per square feet, which is 20% less than the base case. You are able to achieve this by reducing the civil cost, which counts for the major cost during construction. Also, we are able to bring the operational cost under control by reducing the cooling loads and designing the rooms for efficient daylighting. The integration of solar panels and recycling the water, we were able to create a self-sufficient building environment.
As it was mentioned, we are using cross-laminated timber in this industry. So according to the literature review that the team conducted, it will cost 29% higher than the brick wall. So according to recent studies in Indonesia, so for if we are using oil palm lumber instead of a hardwood timber, so it will cost 30% lower to create the CLT. So the cost of oil palm lumber will be 20% higher than the brick wall. So it will get reduced by 9%, but it is still 20% higher. So now if we compare the U value of brick wall, which is 2 watt per square meter, and the CLT wall, which is calculated, which is zero point 0.4 watts per square meter. So the construction cost will be higher, as you can see in the graphs, but the operating cost will be lesser as compared to the base case. So we were able to achieve a 20% reduction in per square feet cost area by using these panels. Thank you.
Thank you, team. You finished well in time and did a great job. Let's hear the jury's comments and take questions from them. Aarti, I'll start with you.
Hello, good morning. Can you hear me, Garima?
Yes, Aarti.
Thank you. So, first of all, I would like to congratulate the team. Great effort with your experience and at your age to be able to put together this design proposal and present it so comprehensively is a great achievement. So, congratulations once again, and I hope you continue to be able to improve on this. Uh, a couple of questions. First of all, about energy. The report seems to suggest some different numbers about energy consumption and come to energy. use intensity later. So right now, I think in the presentation you mentioned a number of 75,000 kilowatt hours of annual consumption, but the report suggests something different. So while my question is why this huge difference, first of all, uh, and the next question that I have about, I'll share all my questions and then probably you can answer me in one attempt. You have mentioned a lot of measures about resilience, such as U-breed and multi-purpose furniture, and also biophilic design to tackle air pollution. I have not seen any evidence of the adequacy of the sizing of these measures. It is not about just placing one plant in a building or one vertical garden. So, what is the scientific basis of the sizing? Have you looked at that? And uh, lastly, is this is about CLT. You were talking, I think this is the main innovation that you have attempted in this project. Uh, and if you talk about the market potential and the scalability potential of this particular construction material or assembly, uh, how do you see the supply chain panning out? Because India is not a timber-rich country. We do not have a huge forest cover, which is the case now in North America. They have a huge forest cover which they can actually use and they want to use it. Also in Europe, but India does not have that case. I remember seeing in your report that you are mentioning that there will be a waste stream, but like, is the supply chain already established, or do you see that there's a potential of the supply chain being established in the near future? Also related to CLT, and that's my fourth question, and the last question is, and I think this is in term of its affordability. I think the per unit cost mentioned for CLT in your report is 150 rupees per square meter. Uh, is that number accurate? Uh, uh, you know, uh, and I would like to know what is the basis of this number also. Thank you. So those are my four questions.
Yeah, thank you, ma'am. So, talking about CLT and the trees, like the plants, trees which are in India. So, we actually found out because of more deforestation, we have less timber to use as compared to the other countries. So, after researching about CLT and not using hardwood, we thought what else we can use. So, we came up with oil palm wood. So, oil palm wood is actually, it will be a byproduct of the oil palm industry. But then, how much is the industry in India? So then we showed a map where we can see how much hectares we have. So according to that, if after 25 years, so this in India I started in around 1980s or 1990. So till now it has completed a 25-year age. So we can use that wood in the industry to make CLT panels from those. But then also we found out the density of oil palm wood is less. So it can't be used as a structural element. It can only be used as a walling element. So we actually did a literature review of how much its density will be. So we found out around 556 kg per meter cube. So it will be convenient to use as a walling material, but not a structural material. So we decided to go with RCC for structural. For costing, we found out some research papers from Indonesia which stated where they are making furnitures and panels or laminated veneer panels from this product, where they stated it will be a 29% higher than the cost of the system. So we actually, from the base case, we took 29% higher cost. And then if we are using an insulating material in the walling system, because brick wall has a higher U value, so the operational cost for the brick wall was much higher. So and CLT it was much lower because the cooling load was reduced when we used CLT in that case. Then talking about the sizing of the UBIT products, it was stated that in a 200 square feet area, if you have one UPREET, it will be efficient. So it will reduce the AQI to 20. So if we have an area of 600 square feet, we will require 3.5 or 4 plants. So we have in each classroom, we have 4 to 5 UBREET plants in the classroom. So if we have 22 classrooms, 20 classrooms, accordingly, we have 150, 200 total plants in the entire building, these products. And also we have green facades and creepers in the railings. So the leaves density, keeping in mind for the creepers, we kept it around 80 leaves in 0.4 per square meter area. So maybe also the difference in the energy value. So in the report, as according to the grids that were given to us, so there were some minor energy calculation variations. So the team redid the energy calculations and came up with the new calculations because there was some problem in numbers. So we had to recalculate the energy performance, and we, after recalculating, we had stated it in the presentation today.
Thank you, team, for answering the questions. Shriti, your turn now to ask any question you have.
Hello, hi. Thank you. Thank you for presenting. It was very well done considering you guys were going first. You usually have more anxiety. So, very well done. Everybody took, the presentation was well distributed among different team members. I liked how you very nicely presented about the water performance, structural cooling. It was the graphics and everything was neatly done. I just have two questions. So most of the answers I think you've already given to Aarti regarding CLT. My just one concern around the material, more so is around the material itself. So palm oil wood usually has a very high moisture content. It's anywhere between 60 to 70%. And if you're making any panel, whether for walling or even thinking of it as a CLT, as an alternative for CLT, you have to bring down the MC as low as 10 to 12%. So that involves a lot of drying process for which you might have to set up a boiler. So how do you see that cost affecting your scalability of this innovation? And the second thing is, I didn't see much in the report around building automation. Since you have a very high, your built up area is quite a lot. I would like to know a little bit more. How do you seem to use, means to bring more automation to the building?
Okay. Yeah. Thank you, ma'am. So about the moisture content, as you said, it needs to be clean, dried in a like clean dried to 12%. So that process is done, but because of that, the embodied energy is high. So we had a talk with right now in the industry. We are in Mumbai, so there are wood market in Lalbagh and in Kurla. So we had a talk on them on call, asking about if you have heard about the oil palm wood. So it was not still heard in the market. So I had a talk with them about if we are using timber, so how do you process it? So can you tell me how do you bring timber to Mumbai? So they have sawmills in different in Maharashtra spaces, and they said if you want something help from us, we can actually come together and see how this product can become here. But they have their drying machines also. So I had to talk with them. This has a very high moisture content, so we need some dryer. So how do you process it? So they said they have a large sawmill when they first dry the timber. So there is sun drying and there is a machine drying process. So sun drying won't be effective for oil palm wood. So machine drying will be very effective. So in this way, we can do it in India if we want to process ahead. For building automation, maybe Nishant or Anjali can answer the question.
For the building automation part, like previously said, we are using radiant cooling systems and various more innovations like hydroponics and all to bring about the innovation part in highlight.
So for the structural cooling, we are also using some thermometers which would be plugged into the which would be inserted inside the slab, so that we get the slab temperature continuously. So that if so we get to know what is the slab temperature and how would it affect the environment at that time. And we also have panels that of individual rooms would have panels outside the rooms that would be from which would be able to connect the cooling inside, like amount of flow and everything. So that is how the water automation for structural cooling will be done. And for lighting, we have planned for sensors in the corridors, especially as corridors won't be used after a certain time, and using sensors would be much better for effective light use also. So these were the automation plans that we had.
Thank you. Thanks.
Harsh, over to you.
Yeah, thanks, Garima. So, firstly, I really, want to thank you for all the effort that you all have put in. So, Amrita, Anjali, Nishant, Ritika, rest of the team, well done for that. So, the way I want to do it is I want to just quickly react to certain things, just for, because we are here to learn. This is, one of the buildings of the many you are going to design, as you move forward into the profession. So, what I thought was quite clear about your project was that you had a very good idea of the tight site that you were designing. Um, I thought you also did a good job at understanding that there are some surrounding buildings which are quite tall, right? I think, and then you try to
Yeah.
respond to it. Even it's a simple form, just to see, but there is thinking behind why you don't put that building block on the west, rather you put it on the east, right? So so that is good. Where I thought that some of the things could have been strengthened was when you explain the numbers, I had trouble understanding the numbers clearly, right? Which some of the charts didn't carry units, right? So what that indicates to me is a certain lack of clarity on that aspect, which is okay, because we all are kind of learning about the science, the building science. What I will do now is I want to not pose all the questions to you right away. I will pose one or two questions and I'll take your kind of reaction to them. Instead of just posing it, because I find it a little difficult to kind of grasp it in. So, first question I have for you all is, if you go to slide 14 of your presentation, there is, I think, a chart on the climate which describes the dry bulb temperatures. Could you go there, Garima? Is it possible?
Yes, Harsh. The teams. You. One second. I'll just. Yeah. You can go to the right slide. Yeah.
Right. So, this is a very powerful diagram because you can actually capture what happens in Mumbai, for the 12 months, essentially, right? And you have identified, from April to September in red, and then, certain portions in January, February, March, and this. So, what I want to ask you is that, can you explain very simply that, let's say there is one classroom, okay, that you have designed. How does that classroom work differently in the red portion, and how does that classroom work differently, let's say, in the blue portion, right?
Yeah.
And second thing I want to say is that, also in this, please tell me the comfort level, the top comfort level, because in the blue you have said period with DBT lies in the comfort zone, right? So what I understand is comfort zone is far lower. DBT in blue is also very high, right? It is not low, right? But you have written low. So there's a lack of clarity in that. And then definitely during, April to September, driver peak temperatures and, even average temperatures, the yellow zone, are quite high, right? So it's pretty high all through the year. But you are telling me there is a distinct difference. So can you explain it? How does a classroom work differently in red zone to a blue zone?
Yes. So in the red zone, so now red zone. So classroom, as we are using a structural cooling system, so the temperature of the slab will be dependent on the DBT, because if the slab on the top is 45 degrees Celsius, accordingly the surface temperature will vary. So in case of April to September, so as you can see, when the temperatures are quite low as compared to the other months, in these, because there is rainy season, so there is more diffuse light, so there will be more less, so it will be around 40 degrees Celsius or 42, which will be less as compared to other months. So then there will be a less pressure on the structural cooling system to actually cool the entire structure. So the users which are sitting inside will feel more comfortable. So there is a comfort range of around 28 to 32 degree, 26 to 32 degree. So according to the red band,
Sorry,
this
26
system will
to,
happen.
could you repeat that? 26 to, how
Yeah,
much did you say?
26 to
What is
around
the comfort band
31,
you have
32
established?
degree.
Okay, all right.
Yes.
Please continue. Sorry.
Yeah.
Yeah.
Yes. So that's how the classroom will vary according to the different seasons because of the structural cooling system. And in this, so when we read this graph, so there are dark gray and light gray, which shows a comfort zone of summer and winter. So it was showing that in Jan, Feb, March, October, November, December, it is somewhat near to the comfort band of summer. But when you see the annual average comfort band, all the temperatures are not in the comfort zone. Also,
Yeah.
if we personally experience Mumbai temperature, the May is the hottest month. So there are temperatures which are higher in May, but the so we personal as well as the technical climate consultant data together and design the system accordingly with the data.
Okay. Any other team members want to say something? I'll just react to it, and we'll go to only one more question, and I'll close it because I'm taking more time than. Do you want to? Anybody else wants to say something? See, my point here is that if your gray portion is your comfort band, then your diagram shows that even in May or so in February, your average temperature, average high, which is the yellow band, yellow portion, is fairly
Yes.
high, right? So it is above 30 degrees C, right? So
Yeah.
what that means is that essentially, you would need to run some sort of cooling all through the year. So what I wanted to hear from you was that essentially you will have to run some kind of cooling pretty much from this diagram, pretty much most of the year, right? You have selected, radiant cooling system, which is, integrated into your structure. Right now, what you would see in this diagram is also, I was looking for you to identify the monsoon zone, which is very typical of Mumbai, right? Which is very high humidity and has very peculiar comfort concerns, right? So it's not about just dry bulb temperature, which you're showing, but humidity becomes an issue during maybe, when the temperatures actually go down. So July, August, right? Peak. It's highly humid, and you want higher air speeds, not just temperature down. So what I would urge you later on as you carry forward this project with the client and so on and so forth, look at comfort as a holistic parameter, not just dry bulb temperature. And Mumbai is pretty strong in terms of if you want to really target certain comfort levels, you have to think of cooling it pretty much most of the year, right? Unless you find ways to relax that standard, right? You say no, we feel that you can go up to 31, right? I feel presently if you are using iMac, you may want to actually stick around 29 operative temperature. So that's okay, fine. Now, thank you for that. Now, last question I'll ask you is that you all have learned some new tools, right? Essentially during this process. And what I wanted to pose you is that after using all of these new tools, how do you think your design is different from a conventional design that anybody else would produce without using the understanding and knowledge that you've gained? So it's a very kind of philosophical question in a way. But what I'm looking for is what are your takeaways from this project?
Okay. So first takeaway was how. So first, when we started with the site, the first thing was how can we reduce the heat gain with the form, which is very essential at initial planning stage. So conceptually, if we have any ideas, so how practically it will be possible? Because if the once the form is selected, and it does, and if there is more solar radiation or heat gain of the form, it will put a pressure on the operational cost. So by using the initial tools of climate consultant and design builder, we decided the form, which will help us to reduce the heat gain. The second thing we went up to after heat gain, the passive strategies of cross ventilation, how the wind will flow, how much wind velocity we'll get, how we can size the windows. So with conceptual knowledge, we sized the windows accordingly. But then if those sizings are working or not, the user will feel comfortable. We got with um, the negative and positive pressure is happening or not, because if we see if there is a building in front of us, it will create a negative pressure ahead of that zone. So we stimulated it and saw that it is creating negative positive pressure, so which will help us for the cross ventilation. So we finalized the form based on it, and accordingly eventually we went ahead with the ideas of then adding some active strategies to it of structural cooling and lighting systems and everything ahead to reduce the operational cost. And
Okay.
then we
Thank you,
will
Ritu.
be yeah.
Okay.
Yeah,
Thank you.
in interest of time, we will have to conclude this presentation now. Thank you, team. Thank you, Team Abhijan. And let's take 5 minutes and get ready for the next presentation.
Thank you, ma'am.
Thank you, man. Thank you, Julius.
Thank you so much.
Our next presentation is from the builders. They have worked on Hamara School in Aligarh. Their project partner is Society for Human Welfare and Education. Let's do a quick AV check for our presenters. Hi Saksham, can you turn on your mic and say something?
Hello.
Yeah,
Hello,
good.
am I audible?
Yeah.
Yeah.
Hi Astha.
Hi, am I audible?
Yeah, good. Hi Anamika.
Hi, am I audible?
Yes, thank you. Hi Sobia.
Hi, am I audible?
Yeah. Can you please share your screen with the presentation on?
The backup presenter can share the screen, right? But I
I
think,
believe yes.
yeah, so they're not there in the show. They are
Yeah,
still
yeah,
backstage.
they can share the screen.
Okay, they can share the screen. Yeah.
Please go on the slideshow mode. Great. So team, you will have 25 minutes to present your work to the jury. At 20 minutes, I will ring a signal like this. You won't have a 26th minute, which means at 25 minutes, I will stop you and ask you to end your presentation. After that, we will have 15 minutes for a Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best.
A very good morning to one and all present here. We welcome you to the final presentation by our team, the Builders, where we present to you our project, the Hamara School. I am Anamika Sarkar, and let me quickly narrate to you the journey of the Hamara School.
The year was 1997. A group of young doctors, while studying from Jawaharlal Nehru Medical College in Aligarh, came in contact with young children doing odd jobs at tea stalls, cycle repair shops in and around the AMU campus. These friends decided to do something about it. They surveyed the area of Mallaka Nagla in Aligarh, from where the majority of these children were coming, and they found a severe lack of education, both formal and informal. So they started giving evening tuitions to a small group of children, with an aim of settling these children into the mainstream schools of Aligarh.
Now, let me take you through our process. Our first step was to identify what the problem was. Then we adopted and applied the Hamara School model to solve the education problem. And then our design team devised and adapted the builder's model to address the building and habitation problem. We identified several systemic problems in the school education system at Aligarh, which included problems of class, gender, reach, and pedagogy. For instance, the class based issues of unaffordability and urgency to earn resulted in high dropout rates. There were issues related to gender, namely poor sex ratios, higher dropout rates among girls due to deplorable menstrual health and hygiene awareness, and the associated stigma. The reach within the community due to insufficient number of government schools, long travel distances, and the safety of girl students traveling these distances was also a problem that we identified. Similarly, with pedagogy, intrinsic problems within the culture of education, which focuses merely on literacy in the absence of engagement, empathy, education, and empowerment of the children, was an issue we wished to tackle. And finally, we had wastage of resources and unsustainable financial models. With the design, building, and inhabitation problems, we identified two main issues, namely the disconnect between the building and its inhabitants and the non inclusion of materials, resources, and non human elements. The Hamara School follows the hub and spoke model of education. This new campus aims to become the hub for various other schools spread across different neighborhoods in the city, where at present there are five. This ensures wider and deeper reach of the school into the community, all while ensuring the safety of the more vulnerable students and short travel distances to school. This increases engagement with the community, and the community and the school become one. It becomes everybody's school. That is why we say, Hamara school is Hum Sabka school. The Hamara School also stands for empathy and empowerment. It focuses on skill building and vocational training, which not only solves the earning problem but also helps control the dropout rate. Additionally, it helps tackle matters of gender sensitization, awareness, health, and hygiene, which addresses the poor sex ratios, girl child dropout rates, and stigma. As a team, we chose to implement certain pedagogic methods which could be embodied by our building. This would help foster an environment of studio based learning in which the surrounding environment itself serves as an educational tool. It helps transcend bookish knowledge and moves into learning from lived experiences. We thought it important to build a connection with the community through shared living spaces, thus interacting with the farmers, villagers, construction workers, and all kinds of people around our school became of paramount importance. This also translated into efficient and diverse utilization of building and infrastructure. The space and time sharing revenue models allows for the renting of unused spaces such as classrooms, labs, multi-purpose halls, playgrounds, health centers into various other uses. So during non-school hours, these spaces can transform into socio-cultural workshop spaces, markets, and public assembly spaces. This aids in financial sustainability and the cross-subsidy model of the Hamara School. To solve the building and inhabitation problem, the builders have adopted a model which takes us from building to dwelling. What this primarily implies is that we give priority to engage with how the inhabitants of the building live and make use of the space. We also give equal importance to matter, material, resources, and the flora and fauna. They have their own agency, which is to be valued, preserved, and included in the Hamara School campus. The sustainability of the community also translates to that of the building materials that we have adopted in the project, such as rammed earth and terracotta hollow brick jalis, sourced from the site itself and made with local skilled laborers. We also include the community who we imagine as co-builders of the project. For example, we use the expertise of Mr. Gupta, Mr. Naeem, and Mr. Ramzani at several stages over the course of the project. This sums up how we have envisaged the Hamara School and its journey to aid in the empowerment of the children and the community within which it stays embedded. This sums up both how the Hamara School team and the builders have together envisaged the project in its empowerment of the children and the community. I will now let Astha take over, who will take you through the architectural design journey of the Hamara School.
In this section, I'll take you through our design process and journey.
We identify the permissible built up areas And then we punctured the building to create a central open space come playground. And then we connected the blocks through a central spine and a wide staircase come social space, energized and animated by this exquisite transformative terracotta block screen. Through the same method of what we have, we zeroed in on the material vocabulary. We built our walls with rammed earth procured from the foundation excavations. Simultaneously, we examined the indigenous skill sets that we have. We saw the potters community, and with them, we built this jali wall from terracotta hollow blocks sourced from the excavated earth and baked on the site. We took it to the next level by adjusting it to light and ventilation. The laying is parametrically developed and gives a fascinating sense of light, shadow, and temporality. We saw the migrant farmer community and the beautiful mud bamboo homes they make, and we worked with them to make community spaces and kiosks. We took the cue from the bamboo and innovated a flexible shading system in keeping with these structures. It evolved from a flat scheme to an elaborate one. It allows for climatic flexibility and creates a childlike, vibrant, and energetic atmosphere. While thinking about the landscape, we ask this question: why can't we fuse the built with the earth? So you will see that the entire land in and around the building is conjoined and the children can just smoothly sail like one does on water. From the playground to the tot lot to the swings and sitting spaces, kitchen garden, and then back through the spine.
Furthermore, we have adopted permaculture to incorporate the flora and the fauna. The circular flow of resources from one user to the other with the conscious inclusion of indigenous flora led to the development of an efficient ecosystem. While the human took care of the soil, the native plants through a gill system not only complement each other's growth, but in turn gifted the humans with food and shelter. Since integration and interconnectedness of various elements into each other became a core objective of our project, and one aspect of it is visible in the seamless flow of our landscape, where the built in very unified manner blends with the earth. Now, let's have a few sneak peeks into the insights. Beyond the binaries and the modes of thinking, Hamara School becomes one holistic community where the social, cultural, economic, and financial all become the same thing. So different stakeholders were brought together to to design and to design and make the building. The building and the inhabitants accommodate each other. The building transforms itself as per the inhabitants' need. Likewise, the inhabitants adapt themselves to fit into the building. So you see the distinction between building and dwelling ceases to exist. That is, that it is our precisely that is precisely our motto: from building to dwelling. The larger programmatic zoning considers multiple discussions with clients to understand their pedagogy and anticipation towards the building and other parameters, which could impact the approach towards co-design. As a result, all the spaces that could be used for revenue generations were kept on the outfront and ground floor, so that the other educational and vocational spaces do not get affected. The keen thought and considerations have been put to make the building sustainable in its social physicality as well. Does the building act? Does the building and its universal access? Does the building and its universal access? Does the building have an universal access to all the elements and consider the need of differently abled people? The client's demand to make use of the off timings for revenue generations become an additional layer for us to attentively strategize a space. There is a provision of the multi-purpose hall with flexible divisions which act as a space for certain vocational activities during the school hours, but could also be rented out to the nearby community in the off hours. Now let's try to unpack the floor plans and understand the design process better, which consider all the factors that are mentioned in the slide, like site, context, permissibility, footprint, and massing within our building. So for the ground floor, uh, the lobby inside the front access provides entry into the building. Large communal spaces like multi-purpose hall and cafeteria invites the individual inside to host community-oriented programs hosted throughout the year. The administrative block, medical center, and kindergarten classrooms are located to the front block of the building. Within the first floor, it entails corridors that connect block to the rear block. The front block consists of educational spaces like studios and library with sitting spaces. The rear block consists of computer labs and classrooms. Each floor has one male and one female washroom, which is also inclusive of differently abled cubicles. The second floor entails a composite science lab with classrooms and spaces for vocational activities such as embroidery workshops and model making workshops. All fenestration systems within the building intend to provide thermal comfort with an attentive adaptability and transformation to the dwellers. Local materials and construction techniques provide an opportunity for co-designing and community engagement. So, to understand the experientiality of the space, here are few renders which we try to provide. This is from the communal spaces. This is from the this is from an this is the kind of interactive spaces which we try to create. Um, so that sums up the story of our architectural design journey. Sobia will now take us through our journey of making the Hamara school a healthy, comfortable place to live. Also, how it's energy efficient and how we made this into a net zero campus.
You are on mute, Sobia. Please unmute yourselves. Please unmute yourselves and kindly repeat. Yeah. Thank you.
Sorry. Energy performance, health, and well-being. In this section, we find the answers to the following question: what strategies do we use to reduce the thermal loads and incorporate passive systems? How do we ensure visual comfort, both daylighting, artificial lighting in an energy-efficient manner? How do we create a good indoor environmental quality, ensuring health, well-being of the inhabitants? And finally, what has been our strategy to compensate for the energy used by the renewable energy means? This was the overall method and the process. To analyze heat gain losses throughout the various components of the built environment, a benchmark scenario of the building was simulated and the results compared to the indicated cases. We were able to reduce the heat gain through building envelope components by optimizing the build form, orientation, self-shading capabilities, courtyard planning, high thermal mass construction, thermal insulation of wall and roofs, and shaded building components. Window to wall ratio 14%, cool roof with pond and high SRI paint plus solar PV shadows, mostly semi open spaces to reduce the demand for air conditioning and hence total energy use. Let me explain how we achieved visual comfort and performance. Firstly, we reduce the lighting energy demands by ensuring daylighting in all occupied spaces, compiling with the Super ECBC to ensure 60% daylit spaces, having more than 90% daylight time. Secondly, we designed a ceiling suspended task lighting, enhancing designing maximum efficiency. We followed NBC standards for elements compliance. Thirdly, we used a high efficacy LED lighting. All the details of lighting fixtures and specifications are in the engineering and operation section. This helped in achieving overall reduction of LPD by 27% over ECBC LPD benchmark. These are the input specification, the daylight model. The daylight simulation of the entire pro model was carried out. Here, I am sharing a specimen simulation of a typical classroom and on the southwest orientation, which is the problematic orientation of the building. In terms of UDI, we were able to achieve more than 60% of the floor area with more than 90% daylit time. The effective shaded and unshaded openings were measured, and accordingly, the shading was optimized. The annual solar exposure analysis was also carried out for glare analysis in order to eliminate chances of solar glare. Similarly, all artificial simulations were carried out on Relux and the results are on the screen. As you can see, 100% of the task area met Lux requirement. This is for multipurpose hall area and nursery. After visual comfort and performance, the third step was reduce plug loads, and for this we used BLDC 28 watts, which were 3 times efficient than the conventional fans of 75 watts. Low EPD, equipment power density requirement of Hamara school also helped our cause. Next up is a complete strategy of achieving thermal comfort and performance. After analyzing the project conditions and discussions with the client, we knew we had to go for low energy passive design system to adopt the India model for adaptive thermal comfort. The first system of the natural ventilation for moderate season. The second system was to use free radiant cooling coming from an evaporation pond which cools the slab. In extreme conditions, this is complemented with the direct evaporative coolers placed inside the space. In the adaptive comfort model, we arrived at a neutral temperature through the equation at the bottom of the screen and the comfort band with plus minus 4 degree. Ventilation is sufficient with the windows to maximum openable areas around 20%. Hence, it was difficult to model a radiant system in Equest or design a builder. With the help of our industrial partner, SMH Adil from GEAT Simulation, we did a mathematical model to predict the temperature of the slab, predict indoor and operative temperature. There is an evaporator pond similar to a cooling system on a rooftop where fountain evaporation cools the water near to the WBT. The water at near WBT, which is 22 degrees Celsius, circulates in the radiant cooling slab. This helps in bringing the operative temperature drastically. In extreme conditions, this radiant system is complemented by direct evaporative coolers, which brings down the inside air temperatures to near WBT, thereby hugely reducing the unmet hours. The nighttime cooling and the sky as the sink helps in cooling the rooftop pond, and the system is open before sunrise to utilize sky and night temperature. This is the view of the terrace. These are the simulations results of the cooling system. This is the stage-wise energy saving. This is the graphical effect of the ECMS energy conservation measures. As you can see, proposed EPI of 13.1 is achieved against the stringent baseline of 27.1. Finally, towards net zero, multiple scenarios were exploded, and finally we arrived at a 1. If net metering is available in Aligarh, which is not the case presently, then a 27 kilowatt solar PV will be installed. The second scenario, which is a present scenario, is to go for solar investors who will install the plant and will sell it at cheaper at 50% rate. The final realistic scenario that we arrived is at 10 kilowatt solar PV with battery backup. This 10 kV is the baseline minimum per day consumption, which is affordable yet takes lighting and fan load. A 27 kilowatt is way too expensive and affordable right now. These are the calculation tables. Then finally, we have the indoor environmental quality. This shows the VOC limits and how to conform to the green building standards. The embodied carbon. We carried out embodied carbon calculations from one-click LSA. These are the input parameters of the baseline and proposed case. These are the embodied carbon footprint reduction achieved through our project. So in conclusion, this is how we attempted to create a holistic and all-encompassing model of energy performance with due consideration to comfort and also embedded carbon footprint. Over to Anamika to talk about resilience.
The key questions for us were, what do we mean by a resilient building? And second, how can we ensure pre-disaster resilient measures as also post-disaster recovery measures? For that reason, we identified certain aspects of the project for which we increased our disaster preparedness. First, we ensured an earthquake resilient building. Aligarh, being in zone 3, falls in a moderate damage risk zone. It means risk, though not serious, is not severe. Though serious is not severe, sorry. For earthquakes, we analyzed and identified possible design interventions. We ensured the coinciding of the center of gravity and the center of rigidity. The center diagram is the actual plan form. We also ensured the recommended foundation depth and design as per the soil investigation. The structural design was also an iterative process, and these are the structural simulations of the final design showing structural resilience. Similarly, to protect for floods and droughts, we looked at future projections of the state of water security in the region. To protect from floods and service future protection from droughts, we suggested measures such as rainwater recharge micro-injection wells and raised plinths. Hamara school is sustainable and net zero in its annual energy consumption. It has a 10 kilowatt solar PV system along with battery storage to take the electrical load of all the ceiling fans and 50% of the lighting load. Therefore, Hamara school is not dependent upon the grid for lighting and ventilation. This is further supported by a 30 kilowatt kVA DG set to meet the requirements of the multi-purpose hall, pumps, plug load, kitchen, and the cooling system in extreme conditions. So in the case of long power outage, the school campus has the potential to become a home for distressed communities. Similarly, climate resilience was critical for us. In hot summers, the building insides and open spaces are well shaded and can be completely shut to the outside blue. The evaporative cooling system ensures ventilation and conditioning. In heavy monsoon, the rainwater is stored and given back to the ground source, avoiding any flooding of the site. High thermal mass walls, efficient solar shading, infiltration-free windows, super ECDC compliance and daylighting are some of the key aspects of the climate-resilient Hamara School campus. The campus is also self-reliable for food needs in terms of storage. The kitchen at Hamara School has ample storage space for food of 100 square feet. This is coupled with an 800 square feet kitchen garden to grow kitchen essentials. It can easily store as well as prepare food for 250 people. Following UNHCR guidelines of allocating 3.5 square meters of space per person in disaster shelters, the big multi-purpose hall can provide shelter and sleeping space to about 50 people, with that being expandable to 150 people if outdoor spaces are also included. This sums up our resilience section. Over to Asta for her work on water performance.
Our praxis here is to respect water as a resource crucial for life on Earth. It means we're trying to not hamper availability of water to other life systems and organisms, therefore giving back more than what we use. Hence a net zero positive campus. So how are we bringing in the idea of building to dwelling within the water performance? We first manage the indoor water reduction, employing cost-effective water-saving fixtures, including aerator, nozzles, and flush tanks. By combining these techniques of reduction with the practices described above, we were able to reduce the indoor water demand by 62%, saving a total of 210 kiloliters of water annually. There, these are the details of various fixtures and respective savings. These are the specifications of the plumbing fixtures. For the outdoor water reduction, a combination of xeriscaping, dryland agroforestry, and drip irrigation was employed to cover all the bases. After this, we focused our attentions on water recycling. The generated gray and black water on site is treated within different channels of a single unit eco STP. The stages of filtrations are on the right side of the screen. Replicas of cow's stomach and eco STP does not use any chemicals or energy to treat the water sewage. Thus, it is treated by a combination of microorganisms, plants, and gravel to clean and return the water. This is the recycled grey water and black water data. With about 90% of efficiency, the grey water is used for flushing, evaporative cooling, cleaning, and black water is used for irrigation within the building premises. A total of 1,666 kiloliters of recycled waters are generated annually, out of which 1,004 kiloliters of water was supplied to the farmers' community located around to use for irrigation. After accounting for the fresh water extracted from the ground, our net groundwater recharge stands at 920 kiloliters of water annually. Since the groundwater quality is good, all the rainwater is used for recharge, thereby reducing the storage cost. Based on peak monsoons, the rooftop rainwater is harvested in a 25 kiloliter underground tank for groundwater recharge. The surface rainwater is recharged to the ground, then 25 micro-injector wells was used as an alternative to rainwater harvesting pits. The rainwater within the building is supplied from the groundwater. Thus, a closed loop of harvesting and extracting water is formed for managing the supply and the demand of the fresh water. A total of 1,519 kiloliter of groundwater is recharged through micro-injection wells. And this becomes our water balance sheets, whereas this is the water cycle.
Engineering and operations. The intent here is to capture the system, optimization, sizing, detailing everything that went into the service and systems. The following systems are covered: the lighting system, electrical system, structural system, comfort system, plumbing system, water recycling, and rainwater harvesting. Talking about the lighting systems, this is the detailed sheet, lighting sheet from Relux. And these are the heads under which they have been detailed. These are the fixture specifications.
Thank
These are
you,
the lighting.
Sophia. Thank you, team. I will have to stop you now. Your 25 minutes are up. And I must say, you delivered really well. Let's hear the jury's comments and take questions from them. Shriti, I'll start with you.
Thank you, Garma. Thank you, everyone, for your presentation. I think what can certainly be said about your team is that you very well figured out the right, sweet spot between community design and affordability. So I think every slide that you had was designed from the objective that the community has to be an equal stakeholder. It wasn't just built by an architect. The every stakeholder was involved, whether it was considering them for the construction spaces, for the materials, as well as how well can they adapt to the new design, including how it can support their livelihood. So I think that for me personally was the heart of the presentation that you guys have presented. I just want to understand on that line, since you have utilized a lot of different techniques, especially looking how it can be local and affordable. How do you think this sort of design methodology and the overall concept that you have taken can be scaled in other geographies? Because in India, considering our context, there are a lot of areas, primary healthcare centers, slum schools. There's such dire need of all of those. How do you think this can be replicated, considering you've been using a lot of localized things at this site?
Thank you for your question, ma'am. So one important thing for our team was to look at the community and the community around as like co-builders of the space. So what we essentially wanted to capitalize on was the skills that they brought to the table. So for instance, for us, it was using a lot of like from the farmers, the kinds of structures and stuff that they were using. So similarly, when it comes to like other geographical areas, they will not be the same construction methods as we have employed, of course, but for any other location, it becomes very important before the team moves into like a design building stage to spend sufficient time engaging with the community to kind of see like what are the different things that they have to offer. For instance, we were also able to use like terracotta and like the pottery mills that we have in the area. So to use those resources that were available to us. So with other geographical areas, without having engaged with the community sufficiently and learned from them, it I personally think might be a little bit difficult to generalize to see how it can be scaled, because what the principle that we're almost following is that it cannot be generalized and it needs to be adapted according to wherever the project is situated.
I would like to add to that and say that in terms of our project, it's more of a replicable project than a scalable project, but also in talking in terms of the pedagogy and how the institution functions and how the institution itself, the NGO itself, the school itself is accommodating the community within the school premises, within the school activities, and how the parents are also acting as the co-builders of the school, how the community nearby is also using that space. So that pedagogy itself is really scalable, and that can be adopted in the various geographical locations. So that pedagogy itself is using studios as learning aids, and how the built environment has been used as learning aids. So we are providing, say for example, so there's a door, and when you rotate that door, there's a protractor and you can learn angles from it. So that pedagogy itself can be scalable. So yeah, that was an addition point to that. Thank you.
Thank you.
Harsh, your turn now. Harsh, you may ask your question, please.
Yeah, thanks, Karima. So, um, I think quick reactions. I thought the start of the presentation was superb. I think you really caught my attention, and the way you used the images and the video was really very well done, right, to capture the jury's attention. I also thought that your exploration on kind of using the community, local materials, local skills, I think is very soulful. And as an architect, I think I enjoyed that. And I would really, really encourage you to kind of use that and propagate that in your architecture going forward. Now, where I thought that perhaps I was looking for these to be developed further was when you really enter the building, because there were only two views that you showed me, which were essentially outside. And I really was toward the end looking for, please show me what happens inside, right? Don't show me internet images of protractors, right? And that you can do it, but show me what you've done it. So that was a bit of a missed opportunity, but well done otherwise. So I will look and feel of the building, actually fits the context. So that's another positive. Now, quick questions. Um, can you open any image or a plan and explain the geometry of the shading device, which is very interesting, that you have created, and how it responds to the orientation? I wasn't able to fully capture the orientation and and what's it doing. Can you explain that? Maybe in a plan at the start, that where are your...
Please make it full screen.
Can we go to the energy efficiency section, please? Where we over there, can you go up where we talked about building fenestration and design of the envelope? Yeah, right above this, above this. We'll get back to this again. Yeah, it's above that. Yeah.
You
No.
can start with a plan, if you want to, because I
Yeah.
wasn't able to understand the orientation, right? Which one, where are you kind of opening these shading devices towards? Which direction? Is it towards north, or is it towards
Uh, our building is actually orientated northeast and southwest, so it is
Hmm.
oriented that way.
Hmm.
And so the concept was to create in such a way that we can avoid the harsh summer sun and incorporate the winter sun, since we're trying to make a sustainable kind of building, so we don't want to use any hi-fi type of kinetic fenestrations. So we use a very simple bamboo method for that. So from the if I could explain, if from the western side, eastern side of the building,
Where is north in that? Sorry, I couldn't read this
so
diagram.
you can, yes, the north is on the top part.
Oh, okay. Where you're pointing, that's north. Okay.
Yes. So if you can, if we focus on it, there are two spaces where our sun will be hitting the most. That is the
Hmm.
front facade and the side facade. We have worked with the side facade with the brick jolly, which cuts off the direct sunlight, as but providing the visual comfort inside the building. And in the front facade, what we planned was to create a actually the whole thing is around the building, but majorly on the front facade, we created the bamboo shading systems,
Okay,
both
I think I
vertical
got
and
it.
horizontal.
I got it. I think where I was really getting a little confused is whether you're opening it, the open portions are towards kind of, towards south, right? That's what I understand, right? They're pretty much towards south.
Yes, our main concern was the southern part. Here we can describe the bamboo shading skin.
uh, to add to that, so how we came to this fenestration system, that we started with a simple grid, and the idea was taken from a bamboo scaffolding idea. When we see them in the construction happens, or some construction, I mean, we have a scaffolding, and that idea was to again incorporate the community with that, because there's no really skilled labor needed to do that. And the idea of transformative building, the idea of adaptability, so that you could actually remove those modules during the winter, and you can allow the winter sun and achieve that thermal comfort that you need. And this is where the whole cycle of a building is to dwelling is being completed. And we have added some pop colors to it to give it a school look, and make it attractive. And similar thing is happening with the brick fenestration, which is there on the other facade, that you saw, that the parametric brick
Yeah.
fenestration that we have
Yeah.
given the jali, but it's also movable. So that again, only the sitting spaces near the staircase, those spaces have a module of the brick facade that is movable. So that again gives the user the authority to set and customize it according to
Got
themselves
it.
and use it.
I got it. I think I'll rush you with that because I have another question.
Yeah, sure.
Thanks for that. I think it's very interesting. I just feel that maybe a little bit more work on, kind of looking at how the geometry reacts to the sun movement and how do you develop adaptability over seasons, right? And various orientations would really take this idea forward. But it's really nice. I think I have a question, which is regarding, comfort, right? So the whole premise of your project is that it's a low cost, kind of development. The project cost will be lower, right? Essentially, and maybe there is a little bit of a relaxed way to kind of organize comfort, right? Because there are other buildings which try to control comfort quite a bit, right? You are relying a lot on passive kind of rhythms and to do that. Now in that, what I thought was really missing, which I was really looking for, is that you are in a composite climate, right? I have lived in UP, right, which becomes really cold during the December months, right? That means in the morning, essentially the kids, December, January, February, right, maybe parts of November, they are coming in the morning at maybe temperatures below 18 degrees, right? And your building is really cold. You've only gone for 14% glass, and on top of that you have some shading, right? So my gut feeling is that you do not have any system to increase the comfort of those people for 3 months, right? You have tried to resolve summers, but there is no resolution for winters. How do you react to that?
I think the whole idea of the external shading getting removed at the time of winters was the key idea that we took forward. So that modules were made. If you must have seen the report in detail, which I've given the joinery detail. So how the modules can be removed in the winter, and just the frame would stay. So I think that would allow the winter sun to come in.
Or do you
Another
think,
part is our
just a
zero
quick reaction to
filtration.
that, just a quick reaction to that is that, when you have movable things, even the most expensive buildings fail in that, right? So the building that actually needs minimum maintenance should try have minimum things. That's my view. I'll leave it at that. It's an idea to be worked. Please go ahead, Sobia. Please tell me.
So actually, we have another concept also, that is the zero infiltration windows. So one of the benefits of that is that it will avoid the cold winter winds. So and keeping it works oppositely in during summers and in winters. So we'll keep the room comparatively warmer in summer and cooler in summers. So we actually had gone to site visit to check this out, check the scenario out.
So, a quick reaction to that is that that doesn't work actually, because you can close your house and the CO2 levels inside start rising, right? When you have 50, 60 students in the space and you close your windows, you produce CO2 levels which will be maybe higher than permissible levels. So productivity, learning falls down. It's unhealthy, and that's the problem with school buildings, right? That a lot of them try to do that in winters without a ventilation system, leading to health issues, right? So my thing is that perhaps some kind of ventilation system in a controlled manner that actually allows requisite ventilation rates in your classrooms should be ensured while you open and close the thing. So that's what I was looking for. Summer is well thought out, I think, and you have multiple systems trying to capture summers. Winters is a bit of a issue. Okay, I'm stopping my questions. I think time is an issue. I would love to have more discussion with you, but
Over to you, Aarti. We can take some quick questions.
Um, Thanks, Karima. So, congratulations, team. I think great work. I'll be quick. So, first of all, it seems that this is still not net zero, but it has the potential to be net zero because you have the space to install the requisite amount of PV in the future. But that would also change the cost dynamics of this building and the affordability. Is that correct?
Sorry, your voice broke. I couldn't hear the first bit of your question. Can you please repeat?
So it seems that it is not net zero right now. The building is not net zero right now, but it has the potential to be net zero, correct?
The question is, the building is not net zero right now, but it has a potential to be net zero. Is that correct?
We have managed to reduce. We are reaching at a point that it could be easily be done in a very sustainable manner, in a budget friendly and sustainable manner, through a very basic passive design strategies, like through shading systems and everything. So
Uh,
overall, we are reducing the energy because we have used very less active energy, active systems. It's
right.
more towards passive
But
systems.
right now it's not net zero. Right now it's not net zero.
Uh, I wouldn't say it's not, but we are almost there. Like it's like a part of it only. Since
Yeah.
we couldn't
And
explain
resume.
it in our PPT, explain into our presentations, but we have actually had the PV modules of 10 kilowatt, which actually is sufficient for our both lighting and fan systems. So it's self-reliable, self-resilient on its own. Okay.
I
The
understand that, Sophia. My question is that if you were to add more PV, I know you have the space to add more PV. It is
Yes.
because of the cost of the building would go up. That's my question,
Yes,
right?
presently. Yes, presently. Since
But
we are not, Aligarh does not have the net metering system. So because of this, we cannot have it on the grid. But hopefully in the future, if we have it, then it is perfect.
okay. Next question is that if you look at your comfort diagram, I think it's in figure 2.2 of the main report that you submitted. It seems that with the radiant cooling and the evaporative cooling system, the indoor operative temperatures are touching 30. Is that correct? Am I reading correctly from there? Figure 2.2 in the report. Uh, my observation is that you're on the brink of comfort margin. And if you are already throwing in active ventilation systems or semi-active ventilation systems, that would not it be better to try to improve this thermal comfort condition, because 30 is like almost sitting on the edge. And I could understand that if one is not using any active measures to manage indoor comfort conditions, but since you are using radiant cooling, by the way, very intelligently, and also using evaporative cooling, then what made you not think of improving it further? Was it the energy, or is it something that just you think you felt that 30 would be very comfortable?
Uh, because, ma'am, we are following an IMAC model, that is Indian model for adaptive thermal comfort. So according to that, they have considered 28 degree to 30 degrees Celsius as the comfort level. So we actually went with that. But I think it can easily be dropped in during not in good method, because we not only have radiant cooling, but we have direct evaporative also during really hot summers. So because of that, it will not only cool, like it will automatically cool the air, because the slab has been cooled down, and will cool the air. So overall, it will drop. That we have shown with in our graph system, that we have also dropped it. And it was also said we had done a calculation over the unmet hours, and it was found that we have managed to, with radiant cooling and evaporative cooling, that we have managed to reduce it to zero unmet hours for the ventilation system,
Thank
comfort
you, Sophia.
system.
Thank you, Sophia. Thank you, jury members. And thank you, team builders. We will start with the next presentation shortly.
I had
Our next presentation is from Team Decipher. They have worked on Raya International School in Bangalore. Their project partner is Indian Academy Educational Trust. Let's do a quick EV check for our presenters. Hi, Vignesh. Can you please turn your mic on
Yes,
and say
hello.
something? Yeah, hi, good. Hi, Chaitra.
Hi, hello.
Hi, Sagar.
Hi.
Hi, Adra.
Hi.
Okay, good. Team, you will be having 25 minutes to make the presentation to the jury. At 20 minutes, I will ring a signal like this. You won't have a 26th minute, which means at 25 minutes, I will stop you and ask you to end your presentation. After that, we will have a 15 minutes for Q&A. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best. You can share your screen. Yeah, your time starts now.
Good afternoon, everyone. My name is Sagar Rajopadhyay.
Good afternoon. Myself Ardra Banuj.
Good afternoon, everyone. I'm Vignesh.
Good afternoon, I'm Chaitra.
And we are Team Decipher from Department of Architecture and Planning, Vishwesvaraya National Institute of Technology. We'll begin the presentation on Raya International School. Our project partner is Indian Academy Educational Trust, and the industry partners are Bhumiputra Architects and Maya Praxis. According to the visual you see, the percentage of hot days in Bangalore is expected to grow from 9% in today's day to 38% in 2050. This climate emergency demands that the way we build and think about buildings change radically. Education is a critical agent in addressing this issue. Students, being tomorrow's citizens, should be exposed to an environment that prepares them for a lifetime of sustainable living. Today's school needs to adopt to an integrated approach across the campus, curriculum, and community. With this in mind, we, Team Decipher, with students from architecture and engineering programs, started to work to bring about a change in the construction of educational building sector, highlighting the needs of the present conditions and the not so distant future. Net zero design building, emphasizing efficiency in usage of resources. The project we took up was Indian Academy Educational Trust Raya International School in Bangalore. The team understood the requirements of the brief and the beliefs of the project partner and came up with 5 design goals. The first was a design which would enable learning beyond classrooms, incorporating spaces where students can learn, interact, and innovate. The school also had to be technology enabled, incorporating automation and e learning, and built on a model where students are at its core. Activities that would add up to a holistic development for students also were a requirement, which led to the team proposing unconventional spaces, like a rock climbing wall. The last goal was to enable the school infrastructure to be used beyond the school hours to uncover the maximum potential of the space. The site proposed for Raya School is located in the outskirts of Bangalore city. The site has a typical form made up of rectangular plots, and the total area available adds to 26,794 square meters. It is located in an area with other existing and upcoming academic institutions. An operable runway being 6 kilometers from the site poses height restrictions. The site is relatively flat with a gradual slope towards north. The Games Academy, with a go-karting track to the south of the site, is a major source of noise along the highway to the west. The climate is categorized as tropical savanna, which indicates pleasant conditions given the high elevation of Bangalore. Analysis of the psychrometric chart shows that 18.2% of the hours are already comfortable, and this can be raised to 64.7% through simple strategies like sun shading. Moreover, since it's a school with holidays during the days with the most thermally uncomfortable hours, the team decided to design a building which was largely unconditioned.
Coming to the architectural design, The site is divided into four main parts. This zoning was done considering the weather effects, terrain, user typology, and external factors such as noise. The entrance into the site is from the main road and creates an exclusive parking space at the entry. This creates a buffer separating the school spaces from the traffic dense main road. The sports areas are arranged towards the southern end, factoring in the noise from the neighboring arenas. The presence of the auditorium towards the flank of the vehicular road also paves way for an activity zone comprising the sports area and the auditorium, which can be leased out for public use. The academic blocks are placed towards the northern side to avoid direct heating up of the zone and also to provide for more open learning spaces. The admin block and the canteen are vital focal points that link various parts of the school. The site plan throws light on the two entry and exit points, very minimal hardscape other than the vehicular roads and pathways, and the solar harvesting potential from the rooftop. Future expansion of the academic areas at a later stage is possible vertically. The courtyards that are also shaded learning spaces stitch together the primary, secondary, and the senior blocks. The double L blocks shield the central block, which houses the labs, libraries, and staff rooms, which are all air conditioned. The shaded corridors and cross ventilation would greatly improve the comfort inside the classrooms. A quadrangle is an informal space for the students to converge and learn. The upper floors have northern lights and shaded corridors. The bridges act as mediums of interconnection between the various academic blocks on the first floor. The northern lights have an incline over which the solar panels are affixed. Now, let us look at some of the principles and strategies that form the foundation of our building design. The first being the north light harvesting by orienting the longer side along the north south direction. The second, creation of tangible and intangible connections through connectors and courtyards. And the third being mutual shading.
Moving to the energy performance. As mentioned in initial slides, there is a potential in this location that with basic architectural strategies, we can achieve energy efficiency and desirable thermal comfort. The three strategies we figured out are orientation of classrooms in north-south direction, grouping of unconditioned spaces, and optimized WWR specific to each facade. Here we can see the courtyard punctures are arranged around the spaces in a way that most of the semi-open and spaces adjoining to courtyards have desirable daylight and shaded at the same time. Based on the strategies and in combination with materials use, equipment selection, and automation, we have optimized our conception. LPD to be 2.1 watts per square meter. HVAC energy consumption to be 83,422 kilowatt hour. Total energy consumption to be 1,74,684 kilowatt hour. And other consumptions are 91,262 kilowatt hour. And our solar generation potential is installed number of solar panels to be 600 and installed capacity to be 180 megawatt hour with an excess of 6 megawatt hour. Potential number of solar panels to be 3,707 with each of 300 watt. Potential capacity to be 1,112.1 kilowatt hour. System efficiency is 30%. Total potential yearly generation to be 611.384 megawatt hour, and potential excess solar energy created per year is 437 megawatt hour. Based on these calculations, the design proves to be a net positive building. Moving on to the water performance. A net zero water cycle has been created on our site where the sum of water used from alternative sources and water recharged to the ground is equal to the total water demand. The use of efficient fixtures, as shown, helped us to reduce the total demand of water in the structure by 27% from base case. The total water consumed in the proposed design is 1 crore 27 lakh 83,425 liters. We are able to harvest 1 crore 44 lakh 11,079 liters of rainwater, with an excess of water harvested as used for groundwater recharge. From the grey water generated, 21 lakh 12,897 liters is used for flushing.
The rest of grey water and black water after treatment is led back to municipal supplies. Grey water is treated via multiple stages of gravity filtration. For black water treatment takes place through root zone system. Overhead tank containing water supply for 2 days and underground tank containing water supply enough for 7 days will be constructed. Rest of the water will be stored in underground aquifers via percolation shaft, which intake a maximum of 194 kiloliter per day.
Now coming to resilience, the risks on the site level as well as the challenges that Bangalore faces in the near future were identified and the strategies to mitigate them were developed. The city's urbanization has led to Bengaluru's land surface temperature increase from 33 degrees Celsius in 1992 to 41 degrees in 2017. The city faces the threat of heat waves, and to ensure comfort during such events is important. The buildings were simulated with outdoor temperatures up to 41 degrees, resembling a heat wave scenario, and the indoor air temperatures were checked for comfort. With the proposed building envelope and increased air movement through window placement and ceiling fans, the temperatures within comfort range, with a mean of 28.5 degrees, were obtained in the academic blocks. The roads are constructed using porous asphalt and the walkways with permeable paver blocks, both with partial infiltration, keeping the impermeable surfaces to a minimum. The blocks planned around shaded courtyards also increase the cool. All these strategies combat urban heat island effect. A multi-model climate change projection shows that the rainfall in Bangalore would increase by 25% by mid-2030s. This means that the building needs to be resistant to floods. The plinth of the buildings is raised to zero point 0.9 meters, which prevents the entry of water into the interiors. In case the flood depth exceeds 1.5 meters, the building needs to be recoverable from the effects of flood. By selecting the materials, characteristics such as drying time, durability, porosity, and the amount of water absorbed were considered. Bioretention swales are designed on the periphery of the site, which enables the capture of stormwater closer to the source, as opposed to a more centralized stormwater management system with pipes and detention basins. This also reduces the cost of traditional curbing, gutters, and piping by as much as 15%. In case of a power outage during floods, a lithium ion solar battery is provided that stores electricity generated from the rooftop solar plant. It backs up to 4 circuits, which includes lights, essential appliances, and services. The auditorium and the sports complex are located near the entrances so that they can be easily accessed and used by public during natural disasters. In order to hold back flood water, these buildings are surrounded by flood skirts on continuous waterproof membranes. Since Bangalore is in seismic zone 2, which is the least active zone, the measures which we took for earthquake resilience were only based on thumb rules, such as simple geometries, which can be further fragmented into rectangles. Now coming to affordability. The team tried to incorporate many strategies to reduce the overall capex of the project to make it affordable for the project partner and its investors. Apart from optimizing building form to reduce heat gain and the cooling requirements, major are brought in the hard costs by sourcing materials locally. Civil costs were largely reduced, which brought most of the savings, bringing the construction cost to 41,610 rupees per square meters. Steel in lintels was replaced by bamboo reinforcements using Dendrocalamus strictus, which leads to a saving of rupees 80 per lintel. The cost of plinth filling materials was reduced by using waste for plinth infills. Recycled materials such as door frames, window frames, secondary flooring tiles were used, and the total volume of recycled materials was calculated. The rainwater harvesting system fulfills demands for 87.4% of the annual demand, which saves annually rupees 7,71,410. Solar panels installed on the rooftop harvest 180 megawatt hour of electricity annually, and this decreases the OPEX exponentially, saving 14 lakh 67,000 rupees annually.
Coming to health and well-being have been prioritized throughout the design through various parameters such as ensuring thermal comfort, reducing noise and pollution, focusing on areas like sensory comfort and indoor air quality. Individual blocks of school are scattered across the site to prevent creating hot air pockets. This allows natural hot air to rise up without any obstruction. To maintain thermal comfort in non-conditioned spaces, passive cooling techniques such as courtyards and reflective roofing are employed. Open spaces and large grounds are used as a buffer to reduce noise levels by planning the academic spaces away from the noise sources. Each space is planned around a courtyard or adjoining to an open plaza, which ensures the blend of nature with the built mass, enhancing the spatial quality and visual comfort. Each space have opening on at least two sides, ensuring cross ventilation of 0.18 cubic feet per minute, which is above minimum ASHRAE standards, and air cycle per hour achieved in classrooms is 3.2. Students and faculty are well connected to nature through courtyards that blend in with classrooms, which helps in boosting learning and productivity. Coming to innovation part, team's primary goal under innovation was to address Bengaluru's rising garbage crisis. With the city slowly choking with non-biodegradable waste, we took the waste sink as a solution. The land below a building's plinth is a redundant element in the local ecosystem and it is unable to use for any biodiversity or growing food. Turning this area into waste storage allows for a more sustainable alternative to landfills. Kinetic floor tiles capture energy generated when people walk on them. Tiles transform footsteps into electricity, which can power street lighting. Each time a pedestrian walks over a tile, 2 to 8 watts of energy is being produced. To make children aware of food is wasted every day, school cafeteria will display the amount of food wasted each day. Taking advantage of competitive behavior of the children, these displays can save waste by rewarding them for best performing class in terms of preventing waste. Looking into engineering and operations part, responding to the project partner's requirement of a technology-enabled school, we incorporated a building automation system which would control lights and dynamic shading devices. The system would also be connected to occupancy and temperature sensors to further optimize shutoffs. Scalability and market potential. Since the site is located in a developing area, proposed school has facilities which are missing from broader community, such as an auditorium, sports ground, pool, and a gymnasium, which can be used community when school is not in use. This creates an additional revenue as a whole. Normal share of specialized structures such as auditorium and swimming pool can be usually be recovered through fees and dues, so this does not incur additional expenses on school. Sufficient parking is also provided near the spaces so that the congestion does not become an issue. Many street festivals and celebrations that are local to Bangalore and hold high cultural significance often overlap with non-working hours of the school, allowing for the school complex to be used as a hosting center. Additionally, to educate the incoming community, to promote a net zero building culture, the open plazas is set up with panels display the breakdown the various parameters of green building. Students, parents, and teachers will be informed on various sustainability and net zero measures implemented in the structure through various display boards. They'll further convey this to a wider audience on how the school acts as a beacon for sustainable design. Communications. Using social media as medium, the team reached a younger audience with memes explaining basic concepts and more mature audience with sustainability hacks they can implement in their daily lives. We'd like to thank our project partner, which is Indian Academy Educational Trust, for supporting us and giving us constant inputs throughout the competition. Also, thanks to our industry partners, Bhumiputra Architecture and Maya Praxis. Finally, thanks to our faculty lead, Dr. Meenal Suravar from NIT. Thank you.
Thank you, team. You finished well in time and did a great job. Over to our jury members for questions. Harsh, I'll start with you.
Can you see me now? Okay.
Yeah.
All right. I think I was thinking I'll go second, so so I'm just noting down my thoughts. But I'll start with something positives. I have reviewed your project over the last few months and deliverables. So what I thought was very good about you guys is that you had a very good idea regarding the architectural planning that you wanted to achieve, so that it's a marketable project in the in the existing kind of context of Bangalore. And I also thought it was very clear drawings and a lot of clear thinking in terms of architectural planning and space allocation. I was looking for more insight into how does it look and feel on the inside, again, because you were in such good position at deliverable 3, that this time I thought you would show me more of what happens on those inside bits. So that's a little bit of a missing piece for me. I couldn't really get the feel of the spaces or the architecture or all the stuff that you were creating. Now I'll start with a couple of questions. I have actually posed most of them to you already, but there are a couple of things which uh, I have been digging, mentally. So you say, can you tell me how much percentage of your building is non-AC? Can you react? I think about 80%.
Yeah, only the admin block is air conditioned and the labs in the academic blocks, other spaces are unconditioned.
Right. So my question there is that why do you think a principal requires an air conditioner but a student doesn't? If yeah.
It was the requirements of the brief, so we just reacted to the brief. The requirements said that the admin block should be air conditioned. That's why we had to provide it.
Right. So that's exactly the point I wanted to highlight, is that you have taken an approach which is very marketable. That is, provide the comfort you can provide and ignore all the rest that's required. So, taking so that gets me to my question: how much, in a typical class, do you think kids are more comfortable in your school than they were in any other school that has a shading device? Have you quantified it in any manner?
We haven't really quantified it in terms of percentage, but the based on the thermal comfort simulations that we ran, so we got temperatures within the comfort range. I think it was 24 degrees in the kindergarten block and around 28 degrees in the academic block throughout the year, also considering the heat wave situation.
Right. Okay. So provided, so I'll leave you with that question. Provided your simulations are showing that you are within comfort level, 29 below, there is no argument for having air conditioner somewhere else where the density of occupancy is far lower than a classroom. So that's my first thing, right? I cannot understand any, developer or a owner of the building will allow ACs in a teacher's room if it was not really required, right? Principal maybe, for some peak day. So now with that in mind, the question I have is that you mentioned couple of analysis which I thought were mentioned a little in the run, right? Okay, we did something, and hence I've taken a very pragmatic approach, but we have an image that so for example, I wanted to question you. There was a heat island kind of diagram that you showed, right? Something about heat island, but the analysis that you showed with it was about something which is happening inside, correct? So how are they related? Can you go to that slide and explain? Maybe I missed something, but I thought they were relatively unrelated, inside temperatures and outside heat island.
Yeah, so this part was about resilience. So we tried to combat the urban heat island effect, and due to the urban heat island effect, the outdoor temperatures would increase in the future. So that would have an influence in the indoor temperatures as well, in the indoor comfort. So that's why we thought that if in case in future the outdoor temperatures in a heat wave situation or due to the factored in the urban heat island effect raised to up to 41 degrees, then what would the interior temperatures be, because this is an unconditioned space, so we had to factor that in. So that is why we ran the simulation with outdoor temperatures 41 degree, and then we could achieve temperatures within comfort range. So that is why we decided to go with unconditioned spaces for this.
So am I getting this right? You took a weather file, which is an existing weather file, and you have simulated, or you have kind of taken a weather file for future maybe 10 years down the line when the temperatures you climate change will be higher. Have you done that? Have you taken a future weather file and simulated this?
Yeah, so we inputted the outdoor temperatures to run the simulation. So we ran it with all temperatures from right from 35 degrees to up to 41. So we could achieve comfort up to 41. Then when it goes to 42, 43, then we start getting the problems.
Right. Okay. So now connected question. Okay, if you do that, that's great. Um, Connected question. Your U value of the walls, as I saw in the report, they are exactly as what you would do in. They were quite high, right? They were not low U values. I don't remember the number, but they were exactly what you would do at building as usual, right? In Bangalore. So why would you go there, right? Especially if you want to kind of decrease the kind of heat gains inside. Why would you not improve the U values of the wall?
I think it was a result of a variety of factors. So starting from the material, so the we chose engineered brick as the material instead of probably more efficient AAC blocks because from the industry partners we got input that in this area it's easier to source bricks as compared to other materials and the transportation cost would decrease in this case. Also, bricks was chosen because of flood resilience. That was another factor because of the porosity, the drying times, and also after drying, whether or not it retains the shape. And these properties weren't favorable in terms of AAC blocks. So we went with this envelope because it was giving us the comfort conditions, and we thought that we didn't have to do more to reduce the temperatures inside.
Okay, cool. So I'll just wrap up my comments. Basically, I thought good effort. There is a lot of learning. We all are making. You are making. I'm making with this process. But one thing I wanted to convey was that as you move forward, I would expect young professionals like all of us. I mean, I'm calling myself young as well. To challenge some of the norms that are being just given in the market, right? You need to say, okay, do children need better environments in a classroom, whether they are thermal or whether they are ventilation or anything else, right? And can you do that in the budget, right? And that would be a challenging question for a building. But to say that okay, this is what the client wants, I could achieve it, and essentially they are roughly in that threshold, makes it less challenging. So I would leave you with that. Be more challenging as you go forward. You've challenged some things. You've learned new simulation tools. Use them more kind of integrated manner in an integrated manner. Okay, thank you. On to other jurors now.
Thank you, Harsh. Aarti, your turn now.
Thanks, Yarima. Uh, Congratulations, team. I think within this group, your report was one of the well composed ones, and really, I think in terms of communication and presentation, you have aced it. So, congratulations there. And keep up the effort. I have a few observations because most of the questions that I had have already been asked by my co-tutor Harsh. Uh, One is that so the concepts and the strategies that you have proposed are logical. There is little evidence to support it in terms of analysis. So my recommendation would be going forward as you work in this field. Uh, Please do attempt to include evidence behind your proposal. Uh, Also, in terms of innovation, I have a comment. Some of the innovations that you propose, like kinetic tiles and all, are actually an innovation of the on behalf of the manufacturer. So one can always question this as whether it is an innovation of the team or not. So I would highly recommend uh, that you focus on innovation that you yourself have thought or developed. And there need not be many. Lastly, I have a question of, this is from the health and well-being section. I think it's mentioned that to combat the urban heat island effect, you have installed solar panels which are going to reflect the heat away from the building. Uh, But the point is, and I would like to know what are your thoughts on this, is that this heat is still going to stay somewhere around. It's not going to be dissipated to the other end of the town or something like that. So, how is it fighting the urban heat island effect in the vicinity of the building or the compound, if I may say so? And that's my last question, and that's it.
Yeah, I think we need to give another thought on this because currently the areas around the buildings are quite underdeveloped. So, and we project that within the next 10 years, the development would start in that area because this is in the outskirts of the city. But then, yeah, after the development happens, then this would be an issue if we reflect all the sunlight on the adjacent areas. Yeah.
Okay, thanks. I'm done. Garima, please take.
Shruti, over to you.
Thank you, Garima. Thanks. Hi, congratulations on your presentation. It was certainly one of the most, aesthetically pleasing, neat, clean, not only the presentation, but especially also the report that you guys submitted. So it was very well designed. So it was very comfortable going through it. I just have few comments because my question was mostly around energy performance, which I think Harsh picked up that your most of the spaces are not air conditioned, but if they are, there would definitely be higher energy requirement, and so I think your base, what you're quantifying is your energy requirement. I think is practically less. It should be more energy that the building requires throughout the year. My few comments are I feel like in the immediate condition of the geography where where currently Bangalore is, the project makes sense, the building, the design. But as you expand and in future period, it might happen that the surrounding, as you said, there's not a lot of population right now around it, but there will be. So in that context, probably we need to do more in terms of better thermal and acoustic insulation, because right now you don't have to be concerned about those things, but 5 year down the line, especially if it's an international school, I'm assuming there'll be more density and more things coming up around that area. Those things have to be, like you have to plan them much ahead later, because uh, it's a school. Secondly, your innovations like waste sink, kinetic tiles. I think on the affordability front, this was one of my comments when I was also going through the report. I feel there could be more local affordable ways of addressing few of these issues instead of kinetic tiles and wasting, because these are not very affordable. So overall your cost of construction per square meter is on the higher end. So that I think can be brought down, considering you're not using a lot of ACs, but these other innovations have a cost attached to it. Thirdly, you're using a lot of brick, you're not using AC. I wanted to know how much is the delta in terms of the fact that it is locally available bricks and you substituted that for AC. How much of a difference is it creating to the overall cost? Is it 5%? Is it much more than that, that you went ahead with a brick which might not be that sustainable? Because now in most of the metro cities, Bangalore, Mumbai, Delhi, ACs has become quite the norm instead of red bricks that people have been using in the past.
And yeah, we don't have a really a number to tell you right now, but yeah, we compared them on many properties, and I think it was a cumulative decision of the team to go with bricks. But I think yeah, we'll work on the figures now to quantify more of the data.
Okay. Thank you, jury members. Thank you, Team Decipher. We will now take a long break for lunch. We will start the next presentation at 2:30 p.m. Team Navrati and jury members, please join back by 2:20. Thank you. Samiksha, can you request your teammates to please join? Hello everyone, welcome back to the education division. We will now continue with our presentations. Our fourth presentation is from Team Navrati. They have worked on Bhandarkar Oriental Research Institute in Pune. Their project partner is Bhandarkar Oriental Research Institute. Let's do a quick AV check from our presenters. Hi Ruchika, can you please unmute yourselves and speak something?
Hello.
Hi. Hi Tamanna.
Hello.
Hi. Hi Sakshi.
Hello.
Hi Isha.
Hi, ma'am.
Hi. So team, you will have 25 minutes to present your work to the jury. At 20 minutes, I will ring a signal like this. You won't have a 26th minute, which means at 25 minutes, I will stop you and ask you to end your presentation. After that, we will have 15 minutes for a Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best. You please share your screen and make it on the slideshow mode, and then we can start your presentation.
Yes, ma'am. Is the screen visible, ma'am?
Yes. Hello, everyone. Thank you for having us here today. We, the students of Bhanubhai Nanavati College of Architecture, were eager to design a viably culturally relevant solution to help preserve India's heritage and make it accessible for peoples of all ages and backgrounds. This institute is a rare model, but important amidst the rapid urbanization, where people are just only beginning to realize the pricelessness of our ancient Indian culture and heritage. To achieve this, we have blended the design values of newer technologies to come up with a net positive energy and net zero water educational building. For this project, we have partnered with Bhandarkar Oriental Research Institute, Pune. The institute was established in 1917 and is a public organization. It is efficiently served as a key center for Indological studies and research. It holds one of the largest collections of rare books and manuscripts in South Asia, consisting over 125,000 books and 29,000 manuscripts. The institute has three beautiful structures, heritage and research vegetation of ecological importance that needs to be preserved. We have tried to stay sensitive to existing context throughout the designing process. The climate. Pune has a tropical wet and dry climate of AW type according to Köppen's climate classification, which further is classified into temperate zones. The average annual temperature in Pune is 24.3 degrees Celsius. By taking the radiation into consideration, the best placement of glazing and possible radiation mitigation has been achieved. The site being highly controlled was a major challenge for the team to tackle waterlogging issues, which have been succeeded in our design process. This climate analysis helped us understand the microclimate of the site, which was considered while designing and using PISA design strategies, which has helped us run the campus efficiently. Next. We've also used native and non-invasive species to maintain natural ecosystem of the site. We've stayed mindful to the existing important trees on the site during the design process, while at the same time utilizing the site to solve water scarcity issues through carefully planned rainwater harvesting system. To stay sensitive to the heritage structures, we've used elements of Vada architecture such as courtyard, veranda, etc. We've combined traditional and modern construction techniques. The provision of sloped roof was made to enable the usage of solar tiles and also as a drainage for stormwater. The ramps and elevators were provided to make the structure universally accessible.
In early stages of design, we started working on our goals and step by step procured energy performance compliance. This includes baseline design, designing building envelope, lighting and cooling, and finally making a structure an intelligent building. For the final proposal, we have achieved an EPA of 21.3. The graph at the right bottom talks about the energy performance index achieved through various strategies that we applied throughout the process. The base case EPI majorly comprises of lighting, cooling, and equipment. Coming to the passive strategies in regards with the shading pattern, we firstly oriented our structures in north-south direction. We incorporated shading through verandas and shading devices, which were analyzed based on sun path diagrams, and also you can see the impact the fenestrations have on the interior spaces. Using the strategies, we could achieve 50 to 60% shade in our classrooms. This planning helped us enable adequate light and cross ventilation with reduced glare and heat. Our main aim is to stay sensitive towards the existing context of Bori and its heritage structures, which is clearly seen through the architectural vocabulary also. We made the use of light colored materials with solar reflective index for minimum emissivity to minimize heat absorbed by the building. We incorporated courtyards for natural ventilation and shaded the outdoor porches raised with high plinth to tackle the waterlogging issues. To optimize the building envelope, we compared various sets of materials to settle on the ones with the best resulting U values while making sure that these materials were local and affordable and also climate responsive. For the roof, we have solar tiles with XPS insulations, so sloping steel decking supported with steel trusses. For walls, we have AAC blocks with cellulosic insulation and external plaster with stone cladding to provide the most comfortable interior spaces. For glazing, we have used aluminum frame low emissivity double glazed windows. Isha, you're on mute.
Isha, you were on mute. Please repeat if you said something.
Hello,
Yeah.
You were on mute.
can you hear me? Okay.
Yeah, we can hear you. Please
Okay.
continue.
Okay. After studying daylighting requirements and its effects to optimize design for energy, we have achieved ECBC and Super ECBC compliance for our library block and academic block to gain user comfort levels. The verandas help filter the direct sunlight exposure and minimize the surface temperature in indoor spaces, which eventually reduces cooling loads. In active strategies, we have used LED recessed panels, energy efficient fans, and CCTV and OLED lamps, which maximize energy efficiency and ensures daylight autonomy of 90% and provide energy efficient fixtures. Also, OLEDs cover all the drawbacks of LED, which include blue light emission, flicker, and discomfort glare.
MMO. We have used mixed mode operations to achieve comfortable indoor environments while minimizing reliance on energy intensive cooling systems. So, to operate the cooling systems as per the adaptive thermal comfort, floating set points are optimized according to IMAP for the mixed mode building design. We therefore incorporated a building management system which analyzes the data and efficiently uses the incorporated management like sensors to reduce energy load. The main reason due to which energy consumption gets increased is the sensible and latent heat load due to the occupants and equipment being used, and reducing load with regions is an energy efficient solution for us, which helps us to use the MMO according to the human comfort. This section here shows the optimization of MMO with fenestrations and cross ventilation. The users who want natural ventilation can open the window along with the indoor cooling facility, and once the temperature starts rising from like 25 to 26 and further to 28 degrees Celsius, the windows are shut off so that the indoor spaces are no more heated and the cooling system works efficiently. For
Comfort optimization. For comfort optimization, we used Cove tool to study various factors. Radiation potential helped us to pinpoint where high performance facade glazing was a necessity. We ensured that all these spaces designed passed the COVID occupancy assessment to encourage social distancing, since it often proves a challenge for educational facilities.
The main reason why we have incorporated radiant cooling in our design is because it helped us cut energy consumption by 30% compared to other cooling systems. There is a biological basis of choosing cool buildings over cool air for thermal comfort, which is proved by humans since Stone Age period. People lived in caves which acted like a cradle and let users achieve a perfect thermal balance with its cool walls. Our heritage structures in India, including the ones at Bori, is a prime example that proves comfort passively without using any energy. The structure stores the solar heat within its huge mass and keeps the interior space surfaces below our skin temperature. The building greenhouse the heat stored in its huge mass into the sky through radiant cooling. Hence, taking this same legacy ahead into modern structures, we are using radiant cooling system. Through the use of BMS, radiant cooling will be used as a primary conditioning system, while chilled water system will be used according to the cooling requirements to meet the comfort hours. And this coupling reduces system cooling load by about 60%. To take precautions against humidity, we make use of DOS system, that is dedicated outdoor air system, as we have a library is as one of our prime spaces to preserve the manuscripts. We also made sure that there is dehumidification optimized structurally by incorporating insulation sheets in the slabs, which will break down the conduction process of humidity and cut off such actions to prevent condensation. According to Pune's climate, we do not require cooling throughout the year, therefore, it is mainly used during summer seasons, also for a short period of while, as the educational campuses mostly have summer breaks. This season has low humidity, and the requirement of cooling is from 12 p.m. to 3 p.m., which compared to the occupancy of overall day and year is very less.
We have used NREL tools provided by Solar Decathlon India for our solar calculations. All extensive energy generations on site are made through solar power generation and net positive design is obtained. The size of the plant that we've used is 340 kilowatt at a cost of rupees 35,000 per kilowatt. The annual electricity generation is 5,10,000 kilowatt hour and annual financial savings are rupees 33.5 lakhs. Finally, these extensive energy consumptions and practices have helped us reduce and if using the energy efficiently with 10 design goals helped us gain a net positive energy design.
This psychrometric diagram represents the adaptive comfort zones. Dehumidification acts as a primary strategy in order to create comfortable spaces using mixed mode operations, which we have incorporated in our design. From the table again, it can be concluded that the entire structure has excellent ventilation with appropriate amounts of sunlight, with the exposure being between 250 to 500 lux. As shown previously, both the structures, library and the academic block also passed the COVID assessment test, which means it is up to the mark with current needs of the general public.
Coming to the innovation, we make use of carbon tiles which are developed by a Mumbai-based startup, Carbon Craft Design or CCD. It is the first of its kind. These tiles are made by using air pollution to help offset the world's carbon emissions at scale through a very conventional building element. This helps us prevent carbon emissions through building materials, thus making carbon tile a commercial solution for climate change action. One carbon tile is equivalent to preventing 1 day of clean air. Coming to pigeon tiles, these are a new approach to electricity generation. As pedestrians walk across the tiles, the weight from their footsteps put pressure on electromagnetic generators that are stored below the tiles, harvesting energy. This can be used to power applications like street lighting and can be a great source of renewable energy.
Solar trees. We wanted to make a statement of clean and green energy which our clients could see on daily basis. The solar trees proposed in our design are a symbol of stewardship designed to complement a rooftop solar system or other environmental investments. It will remind and inspire the users of Bori about the positive change that they are bringing about the environment. Solar trees lifts by Spotlight Solar is a modular design that provides flexibility and enhances landscape of the site.
Now, since Bori lies within the municipal limits, there is a need for composting toilets as these toilets require less water usage and enhance the growth of non edible plants and locations where soil amendment is possible. Foam flush composting toilets collect liquid and solid human waste and processes it into compost, that is fertilizer, which can be used for landscaping on the site or disposed of at a wastewater treatment plant. It provides an alternative to flush the toilets by disposing of human waste while minimizing the use of water by 97%, and the compost can be used for revenue generation. Um, One another innovation that we have used is seed paper. Since Bori has a rare collection of books and manuscripts which should be preserved and protected for a longer period of time till future, implementation of seed paper can prove a very promising innovation.
Water. The water demand is 99 lakh liters per month. Generated and recycled water on site is 101 lakh liter per month. The generated water and recycled on site is greater than the demand supply, and so we achieve a net zero water cycle. 50% generated grey water is used for irrigation and other 50% for radiant cooling. 40% of harvested water was stored and shared with neighbors, and other 60% was sent back to the source or groundwater recharge. Reducing water consumption to half in the designed case as compared to the base case. Rainfall is maximum in months of June, July, and August, and least in months of December to April, which is almost negligible. Passive strategies. Foam flush composting reduces water consumption by 97%. Low flow faucets, urinals, shower heads help reduce water requirements. Zeri skipping with drip irrigation reducing water consumption by 50%. Proposed groundwater recharge is done through injection wells. Water circulation. The water is supplied from the overhead tank. As seen in the flowchart, the recycled water, that is grey water, is completely used for fulfilling irrigation and radiant cooling demands. On the right, we can see that water generated through rainwater harvesting is split into two parts. 40% is stored, which is further outsourced and becomes a means for revenue generation, and 60% is returned to the natural water cycle through groundwater recharge through the use of injection wells. We follow we follow
Resilience. We followed four main sustainability goals: quality education, clean water and sanitization, affordable and clean energy, industry innovation, and infrastructure. Next. Some of our main strategies include thermal comfort, structural resilience, community and cultural resilience, universal design with inclusive design. Next, easy replacement, affordable construction, solar rainwater harvesting revenue generation models, waste disposal and management models, recycling on site, energy and water backup.
Affordability. We weighed costs against various factors such as U value and WWR, and it can be seen in the cost line chart. The solar power generation promises future returns of about 8.3 crore over the next 25 years. Passive measures and efficient fixtures such as radiant cooling and LED lights allow us to keep the energy requirement to the bare minimum, and excess power generated can be sold to the grid. Local affordable building materials help us cut costs of transportation.
For engineering and operations, we have sincerely tried to incorporate all these technologies stated before, and through BMS, we aim to have a comprehensive one one technology under which BMS one BMS which supports all these technologies and a foolproof design.
Scalability and market potential. We have studied four aspects of technology: growth and replicability, user orientation, and investor attractiveness. Experts provide comprehensive engineering and inspection services and quality assurance systems, as well as repair, restoration, and modernization of systems throughout the life cycle of the building infrastructure. Our design can be easily replicated throughout the country by changing the scales and spaces of the building. Even as a global scale, as even though such an institute is a rare model at present, but it's gaining its value, and people worldwide and across all ages are showing interest in the Indian culture. The ability to explore the wide range of design techniques and services in easily affordable to clients is our user orientation. Next, communication. We have mainly used digital media and social media put forth our designs and ideas to the world. Our Instagram handle is at the rate Navrati underscore Solar Decathlon India, which is currently our major assets. We are also planning to publish our report in BNCA Buildtex Journal, which is one of the leading journals of our institute. In the end, we conclude our presentation and we thank you for this opportunity and are excited to put forward our learnings from this journey and apply it in our future. Thank you.
Thank you, Team Navriti. You finished before time and gave a very insightful presentation. Now, let us hear from the jury the comments and take questions from them. Arti, I'll start with you.
Thank you, Darren. Thank you so much. Team Liberty, first of all, congratulations. Your report was a very comprehensive one. Whatever you attempted was quite in detail, and I would encourage you to put in everything on the project. So congratulations and keep it up. Couple of questions and recommendations. My first question is about the voting system. It seems that you have suggested that you will only be incoming the solar panel while participating in services, which, if I look at your plans, you do not have much of.
Aarti, we cannot. Aarti, sorry to interrupt you. We cannot hear you very clearly.
Yes, same here. Can't
Your
hear
voice
you.
is echoing. Is the stream also on or something?
Hold on. Now is it clear?
Yeah, much better. Yeah,
Yes,
please
ma'am.
continue.
So my question is, the surface area of south facing surface area of your roof is not much. It's half of the actual roof area. Have you considered that while sizing the PV system?
Yes, ma'am. So for our roof area, we've only considered the southern part of the roof. And because we were not able to cater to our energy requirements just from the solar PV, that's why we've introduced solar trees on our campus. Because as you can see, our campus has a lot of open area and open landscapes. So the solar trees are the major power generation cells rather than the PV tiles.
And all of these solar trees would be facing, the panels would be facing south.
Yes.
Mhm. Also, I would recommend that you look at your roof assembly still. It is the final stage, but you look at your roof assembly and your wall assembly, especially the roof, because it seems that you have not protected the insulation in the roof adequately. So that is one of my recommendations. Other than that, I have two comments. One is on the affordability of the project. You're saying that this is affordable, and I looked at the calculations and all. But it seems that you are integrating a lot of niche technologies and products in your project.
ऐकू नाही येत.
To be able to achieve affordability despite that is a little hard to understand. Maybe you should look at your calculations once again. And also in terms of innovation, my recommendation would be that these the carbon tiles and the pagan tiles and all, they are someone else's creation, a third party. I would probably rate it as their innovation rather than the team's innovation. So probably when you present to the grand jury, I would recommend that you focus on innovation that is coming from you in this design and not simply a product or a technology that is coming as well. That's it from my side. Thanks.
Thank you, ma'am.
Thank you, ma'am.
Shruti, you may ask your questions, please. Shruti, you are speaking on mute. Kindly unmute yourself. No, you're not mute, but we are not able to hear you. No, I'm sorry, we cannot hear you.
Shall
Shruti,
I?
you're not audible. Harsh, please go for
I'll
with
just continue while she solves the issue.
right.
So thank you very much. I thought you know you presented it quite clearly, right? And I think you were able to organize your thoughts as you move through the report to the presentation. That was not my impression in your report because you have tremendous many great ideas, but I thought the report actually was a little difficult to read. That said, I have a few. The good thing about is that you've taken up a project which is very clear, in its requirements, and I am happy to hear that certain of my questions being addressed in some manner, regarding your library and solar PV areas, kind of trying to compensate with things. However, I need some clarity on certain pieces of work. One is that on slide 15, you passed over it quite quickly. You mentioned you have two systems. Could you just elaborate, right? How do they work in tandem? And then, during, let's say, broadly, summer, monsoon, milder season in Pune?
Isha, could you go on that slide?
Slide 15, I thought it was.
Like, if you could share it.
You're sharing your screen, right? We can't see it yet. Isha? It seems Isha is disconnected. If any of you can do that, I believe there are some network issues that are there.
Or even if you don't have the slide, if somebody can attempt, tell me about the two systems and how do they, how do they operate? What are those two systems? Just, your thinking on that.
So, are you talking about radiant cooling and DOS or radiant cooling and mixed mode operation?
You mentioned that you have two systems. Sorry, is it a DOS that you're saying for
Yeah, yeah,
ventilation?
yeah. Yeah, yeah, yeah.
Okay. So can you explain your understanding on why you required that, and how, because it was connected to multiple issues. You said you wanted to maintain certain humidity conditions in libraries, so you did something to the insulation. So I got a little confused. Maybe you can just clarify the slide a little bit.
Yeah, yeah. So actually, according to Köppen's classification, Pune comes under wet and dry conditions. But then we were also referring different codes. So one of those was ECBC, which said that Pune comes under humid conditions. But
Hmm.
actually, even if we practically see it, Pune isn't humid compared to other cities, and it is temperate. So just in case to create the preventions, we did that. So for the precautions, we thought what could we do for humidity. So we included US system, and also there was one thing that we thought that what if there is we needed dehumidification cutoffs. So for in the slabs, for to prevent condensations, we added insulation sheet so
Space.
that there is XPS insulation sheet so that there is no uh, transfer of the energy from one floor to other floor and then condensation occurs and it will completely damage our manuscripts. That was
What do
the
you
whole
think?
idea.
What do you think would be the surface temperatures of a kind of radiant system? Let's say you have a room and you're putting it, I think, in your ceiling, right? So ceiling ka bottom temperatures. What do you think you will be kind of requiring in a system like this in Pune to kind of meet your cooling requirement? Any
18 to 20 degrees Celsius.
18 to 20 degrees Celsius, you are okay. All right. So it's you're trying to keep it high. I think that makes sense. But it just means that you'll have to probably use a lot of radiant area to compensate for the loads. Otherwise, you'll have to get cooler. And as soon as you start getting closer to 16, there is condensation risk. I think you are absolutely right that there is condensation risk issues, right? Especially if you are opening windows, opening doors, things like that. I think that's something kind of right. Now the question I have is, you have always, for your radiant system, you're always showing the lower floor, right? You never showed me what happens on the sloping roof. Where do
Uh,
you there is no slab there, right? So how do you incorporate
yeah.
your radiant
So
in
yes,
that?
Isha, could you go on the slide which has engineering slide with you? So we have used a decking system. We have consulted our faculty leads. So they helped us design a roof which incorporates radiant pipes in the sloping roofs. So it's a technique of using decking slabs, and the corrugated deckings have radiant pipes running through it, and then above that there is concrete with wire meshes, and on top of that we keep our tiles, and this whole thing is supported by steel trusses, and the whole package also has insulation in it to avoid condensation.
So I think short answer, you're putting it in that slope, right? Somehow and then you have
Yeah, we
some
are protect.
concrete
Yes.
layer on top. One way to look at it would have been, just kind of something hanging down, right, as panels, right, in the space, which may have given you slightly better kind of view angle, let's say, to the human occupants, right? Because radiant cooling also, you exchange energy between body and so that's. I'll leave it there, but I think I get where you're heading with that. I'll request you to kind of explore the upper level a bit more. I had a question that on your water diagram, right? If you can go to that, I'm forgetting the slide number, but essentially you showed. Um, I think it was your water cycle diagram, which was showing to, yeah, here. So what I was trying to understand was that you have your rain harvesting system totally separate from your, from your building system, right? So you are essentially saying that all the rain that's falling down, you are storing it. So either you're putting it in the injection well, or you are selling it for some revenue, right? While you are also taking municipal water supply for your building, right? So my question was that why not use some of the water that's actually on your side? So our overall balance maybe works out, right, in terms of numbers, but you are obviously putting load on the municipal authorities to pump that much of extra water to your site. Why not use rainwater? Because it'll save you energy, right? And you're doing it on site, and that's closer to the net zero kind of aspiration. So could you react to that?
We have to establish rainwater treatment plant for if we are going for rainwater harvesting. If we are using rainwater for domestic purposes.
So you are saying you don't want to establish that. Is that the
Yeah,
cost is
we
a
don't.
concern or something?
Yeah. Yes.
Right. Okay. I mean, that's you may be able to work out the numbers that how much you're injecting, and you might get net zero balance. But essentially, for a person like me, I would probably understand. As a rain is falling, you're trying to use that on your building itself. Seems a little bit more sustainable. You'll have to work out numbers, right? I am not fully convinced about this, but fine. You've taken this approach. I would request you to reconsider it a little bit. The other thing I wanted to point out, which Aarti mentioned, which is a slightly important point. um, I do feel that see, this is a net zero competition regarding the solar PV. You have tried to resolve it as an afterthought, and there's been a little bit of a issue with that. And then what I don't have right now in this presentation is clear numbers: how many trees and how many square meters of trees south facing, what cell type have you put to really compensate the missing roof area to get to net zero, right? So that again is a big question because if you have it, I have missed it, please tell me. मुझे दिखा नहीं इसमें presentation में.
Sir, we've not really added in our presentation, but we did have it in our report in the last deliverable that we've used a total of 44 solar trees on site dispersed along the public spaces or the areas which are going to be used by the researchers, the student, as like leisure areas outside the landscape areas. And about the efficiency model and the numbers, we'll reconsider and work on that, as you said.
Yeah, so I do feel that you are missing PV area, optimized by architects for, generating, right? Now you wanted to respond to the sloping roofs. I do think there is way to chisel and shape the geometry of the roofs while creating more south surfaces, right? Which is what you can explore as you go on. That's all my comments for now. But I wish you all the best and do keep exploring these, right? This project further. As a project, it's quite nice, and the institute that you're working with is quite nice.
Thank you, Harsh. Shriti, please share your comments and questions.
Am I audible, Garma?
Yes. Yes, you're audible.
Okay. Okay, great. Thank you. Okay, first of all, thank you. Thank you for that very, comprehensive, articulate presentation. Everything was very well in a crisp manner showcased. I just have two comments. One is on affordability, another is on insulation. So, taking the point that Aarti mentioned, that a lot of new innovations that you have mentioned are, you know, a I don't think even on a Indian level or global level, there's much commercial viability proven for those techniques yet. For example, especially the kinetic tile. A 2 by 2 tile right now in India costs anywhere around 40,000 rupees, like a 4 square feet tile. So, how do you sort of, consider that in terms of affordability? And if you want to replicate and cover a much bigger carpet area with those tiles to, generate enough energy that can be useful for your sites. I think there you have to look into other ways that are more affordable, more proven in terms of technology. The other is insulation, not just U value, but also in terms of sound, because we are talking about Pune, where there's a lot of monsoon that happens, and those sloping roof does take care of the water not sort of entering the building, and the overhang. How do you take care of the overall comfort inside the building for especially the classrooms? I would just like to know, like, your thought process there. How do you take care of that? Because you've mentioned corrugated sheets and insulation inside, but I think then you might have to add a little, like, another layer to it, or maybe explore some other material, let's say like a ferro cement tile or something else, that might give better insulation there. Just want to know, like, besides corrugated sheet, how do you think you can improve the U value and the acoustics overall inside? Because your whole area is going to get a lot of monsoon. There's going to be a lot of burden on the roof that way.
Ma'am, regarding the acoustics, we actually didn't approach that part of design yet. So I think we'll incorporate it further.
And ma'am, also to understand the approach towards affordability in our case. So we do understand that we are including a lot of new technologies and which are going to cost us a lot in the beginning. But we also understand our project is a very long term project. So the return and investment ratio is going to cater to the investments that we're making right now. As you can understand, today Bori is 100-year-old building. It's 100-year-old institute, and it's going to stay there for the next 100 years probably. So
Yeah.
if we inculcate these new technologies right now, the returns that we'll get after a few years would be more, and hence we think our project is affordable in this approach.
And have you calculated some of those numbers in terms of, like what sort of break even you're looking at, 5 years, 7 years, in terms of using these
Yes,
new
we've made an
technologies
estimate
to
for
improve
25
projects?
years,
Okay.
and we've talked it with our project partners, but that is
Mm-hmm.
still under, like, it's still under the process. So
Okay.
that's all.
Thank you, Team Navrati, and thank you, jurors. We'll now take some time to start the next presentation.
Thank you.
Hello, Team Renovo. Our next presentation is from Team Renovo. They have worked on an academic block in the Institute of Medicine Tribhuvan University, which is located in Kathmandu. Their project partner is Tribhuvan University, Kathmandu, Nepal. Let's do it. Let's do a quick AV check for our presenters. Hi, Ishika. Can you please unmute yourselves?
Yeah, hi.
Hi. Hi, Chitra.
Hi.
Hi, Jayesh.
Hi.
Hi, Kiranjot.
Hi.
You can also start sharing your screen on a slideshow mode. Team, you will be having 25 minutes to present your work to the jury. At 20 minutes, I will ring the signal like this. You won't have a 26th minute, which means at 25 minutes, I will stop you and ask you to end your presentation. After that, we will have 15 minutes of a Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best.
Thank you. Okay, so good afternoon, everyone. This is Team Renovo, and we present to you our sustainable design solution for academic block, Tribhuvan University, Kirtipur, Nepal.
Our team comprises of 10 members from third year of Bachelor of Architecture and 2 members from first and second year Building Engineering Management from School of Planning and Architecture, New Delhi. Our team is advised by Professor Dr. Shweta Manchanda. I am Chitra Tiwari.
Myself, Ishika Meena.
I'm Kiranjot Makar.
I am Jayesh More. And on behalf of Team Renuvo, we will present to you our project.
Going into this challenge, we had a set of broad goals we wanted to achieve in this proposal. These goals varied from tackling the hilly terrain of the site well and responding to the climate and the context, to making the building a net zero energy as well as a net zero water building. To give a brief description about the project, we designed the academic block of Tribhuvan University, Kirtipur. Tribhuvan University is a public university located in Kirtipur, Kathmandu, Nepal. Established in 1959, TU is the oldest of the 6 universities in Nepal. Tribhuvan is a non-profit autonomous institution funded by the government of Nepal. There are 4 research centers in TU. Being one of the largest universities in the world in terms of its size, it offers wide variety of programs and practices.
Located southwest of the Kathmandu city in Kirtipur district, our site is a medical research institute which is connected directly to the main hospital block, which is present in the vicinity of Bagmati River along the ring road. The design is of the academic block, which is part of the master plan of new extension to the TU campus, which includes hospital, residential block, and trauma center. After a thorough site analysis, we went to perform a SWOT analysis for our site. We recognized all the strengths and weaknesses of our site to create a proposal that caters to every problem. For this project, our aim was to have a comprehensive design which incorporated the principles like passive design, biophilia, user safety, and security. The design of the academic block was fundamentally centered on segregation of occupants based on their profession on their arrival to the building block, whilst also having a common space to make them feel connected. Vertically, the building is divided into 2 zones: academic zone, which have lecture theatres, examination hall, and library, and administrative zone, which have admin spaces. These 2 zones are connected with the atrium, which acts as a bridge between the both. Laboratories are more private, so they are strategically placed at the top floor to cut off the crowd. After analyzing the contours on the site, we identified the buildable area on the site. Then the built mass was lifted up following the profile. Next, an arrival plaza was designed to create an insertion into the built form. This plaza will also act as a place for recreation for the occupants. A similar insertion was made from the back to visually let in the landscape into the built form. Lastly, an atrium was scooped out to have light and ventilation blend into the interiors. The Tribhuvan University academic block includes facilities like seminar hall, libraries, cafeteria, open-air theatre, and 9 state-of-the-art laboratories. There are 2 pedestrian entrances to the site and 2 vehicular entrances, one of which leads to the drop-off zone and one directly to the parking. The underground parking can accommodate up to 70 cars and 70 bikes. Stepped open-air theatre is located at the southwest part of the building along the profile and has direct access through the atrium. Different entry points were given at the plaza, guiding occupants into designated space, which is with a proper drop-off zone. Ground floor has functions like library, seminar hall, cafeteria, and a few admin spaces. Lifts and staircases are placed near the atrium for ease of vertical circulation. OET has direct access from the atrium. Landscaping is merged into OET, which adds to the view from the seating of the cafeteria. The atrium has a seating staircase, essentially for the students to commute to the lecture theatres and examination halls. The first and second floor has lecture theatres and examination hall on the left side of the atrium and the admin spaces on the right. Breakout spaces among classroom and examination are given to break the linearity of the corridors, which also add on to the overall experience. The third floor has laboratories, quality management, and storage rooms. A direct connection to the main hospital block is given at this level for faculties and doctors to commute to and fro. The atrium in the middle of the building is a primary source of natural ventilation for central recreational space as well as an important source of solar heating within the building. Apart from lighting and heating strategies, natural ventilation is also utilized to the atrium. The atrium will also connect students to the library and cafe. Nepal has a humid climate for almost 50% time of the year and heavy rainfall during the monsoon months. Considering these climatic factors, we opted for a terracotta ventilated facade system. Northeastern facade is made up of modular type of shading devices which cut off east sun using louvers. Planters are inserted at the window level to help simulate connection with the outdoor, adding to the well-being of the occupants. To have an interactive feature in the academic zone to help students to connect to each other, a seating staircase is designed as a key element. This seating staircase will be the primary way of circulation for the students to commute to their classes and examination room, as well as act as a space where they can hang out in the break time, making atrium space full of life and energy. Apart from taking care of all these fundamental aspects, we also wanted the building to respond to the climatic and surrounding conditions in a holistic way. We introduced a bunch of strategies and elements to make building comfortable.
Coming to the atrium facade consists of two layers, a terracotta jali and a glass wall, whose openings can be adjusted as per ventilation requirements of the interior. One of our main focus was to provide maximum filtration through natural mediums wherever possible, and for the same, we planned on creating a green barrier using native plant species on the northeastern facade. This physical barrier cuts down on the sun in the summers and also provides PM filtration. The atrium is our main central space, and it's being naturally ventilated. Plants encouraging dehumidification and producing oxygen were planted throughout the atrium. This helps in keeping CO2 levels below 1000 ppm, which is as per ASHRAE standards. The DOAS unit placed on the roof takes in fresh air directly after it goes through a terrace garden surrounding the unit. The vegetation chosen, black pine and golden dhupi, are native and are known to assist in deposition and removal of particulate pollutants as the air passes through the leaves. System has been laid out in a way to provide suitable air pressure, velocity, and temperatures in the spaces. For the same, the fresh air supply ducts have been placed in the lower end of the wall and the exhausts have been placed on the ceiling level. Furthermore, media filters have been placed in the ducts as they are good for filtering out bacteria and fungus as well as the remaining fine particulate matter. An adaptive comfort model was developed in accordance with ASHRAE standards for the specific site, which allowed more hours to fall into the comfort temperatures, decreasing the need for HVAC. After the initial analysis, it was found that for our case, around 26.7% of the operating hours, the climate is comfortable and can function without the use of any conditioning system, besides the use of ceiling fans or opening of windows. 18.4% of the hours are cold and 24.5% of the hours are cold and humid, indicating the need for both heating and dehumidification in the months of November, December, January, and February. 22.8% falls under the extremely humid conditions, indicating the need for ventilation and dehumidification in the months of June, July, August, and September. And in the months of March, April, and May and October, more than 50% of the hours are comfortable and occupants can attain comfort using ceiling fans. Proposed system for our institutional building is a combination of ground source heat pumps along with a dedicated outdoor air system, which is a DOS system. While the ground source heat pump takes care of the latent heat load, the DOS system takes care of the sensible heat load. Two systems have been deployed for the institute where they work parallelly instead of letting one system take on the load of Kathmandu's cold and humid weather. The plotted graphs show temperatures achieved with and without HVAC using simulations. We notice that most of the operative hours when the HVAC is running lie within the comfort band, proving the achievement of comfort within the built form. Comfort set point and setback temperatures have been set according to comfort analysis, according to ASHRAE 2019. Based on our study, we derived an hourly thermal comfort band for the entire year. This helps in decreasing the overall loads on the system. Through multiple iterations and simulations, we see that after incorporating passive strategies, enhancing the building envelope, and incorporating our proposed HVAC system, a reduction of 68% in the heating loads and 84% in the cooling loads of the building. DOS system itself was responsible for reduction of the cooling and heating loads by 50% due to the presence of a desiccant wheel, which helps in heat exchange between the fresh air supply and the exhaust air. For the biodegradable waste generated on site, we've proposed using vermicomposting to generate rich manure. The non-biodegradable waste, however, had to be treated in a proper manner due to its implications on the environment. We proposed a material recovery facility, an MRF, on the site to deal with this. This MRF is a manual facility where the people will be employed to work. These people will be responsible for the segregation, storage, and the delivery of the waste outside the facility. This led to 75% of the waste being recycled and sold, thereby implying less pressure on the landfills. Coming to the structural system, we proposed the structural system in a maximum span of 8.5 meters, and after extensive load calculations and analysis, column sizes used are 1200 by 1200 meters, and the beam sizes came out to be 300 by 850 mm.
Moving on to the energy performance, we did a solar radiation analysis on the basic massing model of the building to interpret how much radiation will be received by the different facade angles of the building. Using this data, we designed the shading devices for the different facades of the building to avoid glare and excessive heat gain. Nepal has a humid climate for 50% of the year and heavy rainfall during the monsoon months. Considering these climatic factors, we opted for a terracotta ventilated facade system. During summers, where it tends to get uncomfortably humid, the terracotta facade, which is porous in nature, can absorb the moisture and help encourage evaporative cooling. During months of winter, the facade retains heat due to the air cavity while not letting the accumulated heat out. Due to terracotta's high water absorption capacity, it acts as a rain screen and draws moisture away from the structure and protects the hempcrete wall while preventing rise in humidity indoors and maintaining a steady temperature inside. In terms of daylighting, for the base case, we have considered the window wall ratio as 40%, have no shading, and have single 6 mm glass panes. Also, there is no shading devices installed for the atrium skylight. Now, for the proposed case, the window wall ratio is reduced to 30% with appropriate shading devices being added and configured for each facade using Solar Tool and external software. The atrium is being shaded using a tensile structure to ensure soft lighting in the space while increasing the UDI percentage. Using the standard steps provided in the ECBC 2017 and with the help of Design Builder, we have analyzed the daylighting factor of our building. Here we can see the overall UDI maps of our building. The area in black, which is either less than 100 lux or more than 2000 lux, which is undesirable, has been reduced in the proposed case, depicting the increase in useful daylight and reduction in glare. Quantizing the daylighting factor according to the UDI maps above, an increase of 23% has been achieved, thus achieving the ECBC Plus rating for the proposed case. In order to reduce energy consumption in terms of artificial lighting, energy efficient fixtures were chosen. A manual calculation of lighting loads was done for a base case and our proposed case. For the base case, the load came out to be around 84,000 kilowatt hours. For our proposed case, after using energy efficient fixtures, the lighting load came down to 54,000 kilowatt hours. A manual calculation for equipment loads was also done to determine the EPD of different spaces in the building. After all the simulations, a final energy consumption comparison between the base case and the proposed case was done, where we observed an overall 25% decrease in energy consumption. In order to meet the energy requirements of the building, we have installed a solar panel system which produces enough energy throughout the year to make our building a net zero building. In order to account for the fluctuations in energy generation by solar panels throughout the year, we have used gross metering connection to the grid.
The goal to develop a net zero water building was achieved thanks to the abundant rainfall in Kathmandu, Nepal. Water for domestic use was collected from the roof surfaces and hardscapes. After an analysis of the drainage and contours, a location to the south of the academic block was identified and proposed to be built as an artificial pond, storing harvested rainwater all year round. The harvested rainwater is filtered and stored on campus for daily potable use. The grey water generated through domestic use is recycled for use in cooling and irrigation, and black water is treated and then used for irrigation. By using efficient fixtures and appliances, we were able to reduce per capita consumption by over 74%. During monsoon season, abundant rainfall ensures sufficient water supply for the users. However, in the drier months, Kathmandu experiences little to no rainfall. In these months, the reserve from the monsoon months stored in the artificial lake helps in meeting the water requirements. With a roof surface of 3,500 meters square and runoff coefficient of 0.85 and hardscape area of 2,500 meters square and zero point 0.7 runoff coefficient, we get an effective catchment area of 4,725 meters square. To store potable water sourced from the artificial lake for daily use, two 108 kiloliter tanks have been provided on campus. Wastewater is filtered using two methods, DWATs and constructed wetlands. Constructed wetlands are incorporated as a part of the OAT landscaping design, and they work on the principle that plants, microorganisms, and substrates naturally filter and purify water. DWATS combines the physical and biological processes of filtration, that is sedimentation, flotation, aerobic and anaerobic treatment. Constructed wetlands, therefore, form a part of the filtration process in DWATS. Native species of plants were incorporated in the landscaping to reduce unseasonal irrigation loads. Drip irrigation systems have been introduced to increase efficiency and reduce water consumption. Species promoting bird diversity have been proposed to be planted. By using climate responsive and regionally appropriate native species, efficient irrigation methods, almost 22% of reduction was observed in water consumption when compared to the base case. To conclude, for water positivity, the final numbers are as visible on the slide. Our location is in seismic zone 5, which means it is prone to frequent and destructive earthquakes. To make this building more earthquake resistant, framed construction and shear walls were used, expansion joints were installed, and various escape points were provided for speedy evacuation of the people. The zoning of the building has been done in such a way that the functions that receive the highest foot traffic have been shifted to the lowest level. During the monsoon season, there is a risk of cyclones and severe rains. The foundation design of the building has taken this into account. The central atrium reduces the wind force and pressure on the roof, and terracotta rain screen is utilized as a weather-resistant barrier on the facade. A well-designed and well-maintained gutter system to ensure that there are no blockages that result in flooding on site. Faulty equipment and overloading appliances may lead to fire threats. To make our building resilient to fire, we have given fire escape stairs, fire extinguishers, and water sprinklers at regular intervals. Evacuation plans have been placed on every floor, and individual AHU systems are placed on each floor to prevent smoke from spreading from one floor to the next. A DOS has been used in our internal spaces with touchless technology to prevent the spread of infection, a time delay of 5 to 10 minutes between the persons arriving and departing an area, and using pressure differentials to maintain airflow across the zones also helps in preventing the spread of infectious diseases. The building works to minimize air as well as noise pollution in and around the building by use of appropriate plantation around the building and proper sound insulating materials. The building meets water as well as the energy demands of the occupants and at the same time does not harm the groundwater levels or electricity power grid, thus achieving our goal of water and energy sufficiency.
Moving on to innovation, looking at the poor state of solid waste management in Kirtipur, we thought of incorporating an innovative waste management feature to our proposal. We are proposing a material reclamation facility within the site which will benefit the stakeholders, provide extra funds, and is eco-friendly. Another innovation we proposed was the biosolar roof system. It works by combining the two technologies, solar power and green roofs. The microclimate around the panels is important for the functioning of these panels. If it is too hot, the panels can lose their efficiency. The green roof element have a cooling effect from the evapotranspiration and reduce pollution around, which enables a higher efficiency of PV panels. Year-round, green roof can help to keep ambient temperatures around the panels at or near 250 degrees Celsius. This is the best temperature for solar panels to work most efficiently. Since this is a super specialty institution, we wanted to uh, we wanted to maximize the comfort of the place where the students will spend the majority of their time, which is the labs. In order to do so, we're proposing a lab monitoring system which will work towards monitoring the conditions of the lab and then providing 24/7 feedback to the management. Moving on to the scalability, we set up a material recovery facility on site for solid waste management. Kirtipur does not have a proper waste management system, so this approach reduces the pressure on the landfills by 75%. Apart from the landfills, the waste is currently also dumped on the banks of River Bagmati, and setting up a community level MRF will also protect this major water source from further pollution. We can set up an MRF at the Tribhuvan University campus level, and in future, at a community level expansion is also possible. The proposed LMS system has paid special attention to the labs, but in the future, as the pollution increases and the budget for infrastructure also increases, we can expand this monitoring system to a building scale or a campus level as well.
The cost of construction for proposed design is 513 million NPR, which is almost 44 million NPR more than the baseline. There is a major increase in the cost of MEP services and civil works due to the added cost of installation to reduce the embodied energy, such as PV panels, alternative materials, and hybrid construction. This increase in cost can be justified with the life cycle cost. This graph shows the overall cost breakdown of the project. Here we can see the proposed design is 9.3% more expensive than the base case, but due to a reduction in the operational cost uh, of the proposed design to almost half, the life cycle cost of the proposed design over a period of 10 years is decreased to almost 25%, which means we are able to save 275 million NPR over a period of 10 years. To achieve this reduction in cost, we have used some design strategies to every step possible, like rainwater harvesting system that makes the project net water zero consumption and solar PV panels which give us 4.9 million NPR saving per year with a payback period of 9 years.
The main goal of this project was to create a building which brought comfort of one's own home into the institute, with net zero energy consumption and a building which can stand its own ground. We are paving the way for a greener, sustainable, and conscious future for Nepal and its citizens.
We would like to conclude our presentation by acknowledging our project partner, Tribhuvan University, for trusting us with this project. We would also like to thank our faculty advisors for guiding us throughout the way, our industry partners for providing their valuable inputs, and the Solar Decathlon India team for providing us with this great opportunity. Thank you.
Thank you, team. You finished well in time and must say your team did a great job. Let's hear the jury's comments and take questions from them. Harsh, shall we start with you?
Yes. Second. Can you see me now? Yeah. Okay. So well done, team. I think it was definitely very comprehensive approach. So you have, I could see that in the report as well, that you've really made effort overall on the project in various aspects, right? And there is a lot of detailed thinking on energy, water, right? That's there, right? But my I think job is to raise some questions, so I am going to do that. And so what I really thought was very positive was the fact that you had a very clear way to organize, your thinking about the architecture. It's relatively simple. There are some big moves that I, as a juror, felt okay, I could kind of relate to them. Where I thought, while you have done a lot of work on it, where I thought architecturally I wasn't really satisfied is the way you develop the facade and the shading systems, right? They do become rather very similar on all the sides. While you're telling me that you're really trying to kind of address various orientations, so there was, I mean, architecturally, right? You probably could think about that. Now, I have a couple of questions, which are more like trying to understand some things I couldn't get very quickly. So, one is that can you help me understand a couple of pages that you showed? One was, I think, page slide 24. There was something about, like, of course, the dual system that you have, radiant kind of heating and a DOAS. I think it was 24, probably. Yeah. So, I think what I understand about Kathmandu is essentially it's pretty much a cold place, but there is some amount of summer. And I do know people who run air conditioners in Kathmandu, right? Whether in residential buildings or otherwise. So my question here is: firstly, do you have any air conditioned portions in your plan at all, like labs and stuff like that?
So we're providing a DOAS system with a desiccant seal, which would be like providing heat exchange from the internal external, and so that'll have like a heating and cooling coil present, which will not be
Mhm.
like very like not be excessive heating or cooling, just amount like little amount required, because the labs especially would be requiring heating and cooling because of the equipment load. In the summers also they might require cooling, so we wanted to provide that there. So we're not using radiant flooring for the cooling, but we're using the DOAS system for that.
Okay, that's a clear answer. That for the denser spaces, you essentially have
Yes.
what and that, was that because too much of equipment load and and people inside the labs,
Yes,
or
because when we were doing the simulations, we were realizing that especially in like the computer labs and the research labs, the temperatures that we were achieving were a little higher, so we had to provide something.
okay, and the DOA system in terms of not the heating or cooling coil, but just the ventilation supply, right? Are you attempting that for the non-air conditioned spaces, right, or non-heated spaces? So is
That'll
is
be
the
throughout
ventilation
the
in the whole
building.
building being supplied by some kind of mechanical means? Is that how you've worked it
So,
out?
so except the atrium space on both the sides, the admin block as well as the academic block, yes, the DOS system would be provided.
Okay, so okay, and why did were there any spaces you could have totally left for natural ventilation, or because I'm assuming you're not really heating it, cooling it, right? So and you don't have a
We're
very
heat.
wide building. Sorry, you are heating
We
it.
are heating it. Yeah, we
You
are
are
heating
heating it.
it.
Yeah,
Yeah.
you are heating it by the alternate system, right? But you're not cooling it,
Yeah.
right?
No.
And there was no way you could have thought of a system where you're just opening windows for to ventilate. You have a pretty narrow building, right? How wide is it, overall?
About 20 meters, I think.
Yeah, so not
20
that.
minutes.
Sorry, how much is that?
20, around 20.
Right. So that was a thought in my mind, that whether you could have actually got rid of actually the ventilation supply, right, where for the non-air conditioned stuff, saving some energy, right? The other question I had on your report was, how did you account for the hot water requirements? Especially you have labs, right, and there'll be change rooms, right, for doctors coming in, and site energy, right, that lights and the facades. It may be a small portion, but have you gone to that detail?
So for the per capita consumption, it was taken into account, but the way it's being heated has been taken into account for the energy in the energy section. If that answers your question. So
No, I
while we were
meant,
calculating, yeah, sorry.
so I didn't mean the the hot water for the heating of the rooms or something like that. I meant for service hot water, right? Taking a hot shower, right? That demand of hot water, is that also accounted for in your, and other
Uh,
ancillary demands like lifts? You have a tall building, you have lifts, you have facade, you have stuff on site. Um,
so while we were calculating the total water demand, we did take that into account, but it was very minuscule in comparison to the other things that were required, because it's only in certain spaces, for example, the changing showers and all. So heating and all is done right there. We didn't have any elaborate system for that. because that wouldn't have been feasible or made sense.
Well, I think it's not a negative comment. It's something that's developing right on your project. I think you need to now, since you've reached a certain stage of resolution, I think you need to start incorporating other smaller elements which do make a difference, like lifts, right, and hot water demand, right. You have a ground source heat pump, perhaps that can suffice the requirement for hot water, or maybe you decide certain amount of PV area needs to be dedicated to solar thermal, right, which you have a full option for. So um, that's it. And one last question I have is this innovation, bio solar, where you have the green roof and the PVs. I think you call it bio solar roof or something like that. So this, so I wasn't personally, very convinced about it when I saw in the report. So my question is that there are two things. You're telling me Kathmandu is not very hot; it just gets to 30 degrees, right? Maybe heat island effect, couple of degrees up, right? Versus your site is nowhere in the heart of the city. It's actually very green and very open. Then why go for this move, which is going to be very high maintenance and may not have any benefits, right? And then innovate on that, right? Or call it as an innovation. So it's a little bit of a, let's say, thing that I felt it's really not innovation. There were so many other opportunities you could have explored on your project. You can react
Yes.
to it, right? You can react
Yes,
to
sir.
it, that
Yeah.
why you felt it was important.
So when we did the solar radiation analysis, we saw that the roof will receive a lot of glare and a lot of radiation. So we wanted to create incorporate a system that will maximize the lifespan of the PV system. So it degrades with time. So we thought that if we incorporate the system, then maybe we can make the PV system last a bit longer.
Okay, cool. Something for you to think about as you move forward and consider it as a solution. I'll pass on the mic to the other jurors. Thank you very much. Very interesting.
Thank you, Harsh. Shruti, let us hear from you.
Sure. Thank you, Garima. Hi. Congratulations. I think overall the architectural design of the project was very marketable, very clean. Your in-depth analysis, especially for energy and water, was commendable. You had taken care of everything. Everything was very well represented, both in the presentation and the report. I loved the part regarding solid waste management. Uh, that was very welcoming and fresh. That you considered that, and also the calculations that you did, how much of it could go back and maybe create some of the livelihood that is there. My comment or question is mostly around resilience, since your site is one that is in Nepal, in Kathmandu. So besides considering a lot of issue around flood, have you considered that both your roofing as well as walling, since you have a lot of jali as well, you might need an additional layer of vapor and water barrier? There's That was one thing, like, just want to know what did you think about it when you were designing. And second is, there was a lot of discussion around vegetation cover. You even have vegetation on the roof for the biosolar. But maybe graphically, how it looked to me was that there was less landscaping around the site that was there, which I think could have been increased, considering if there's so much heavy rainfall, there's also chances of landslides. So you could have, better sort of enclosed your structure, because the length of it was spread around a lot. So mostly around waterproofing, landslide, as well as the indoor air quality. How do you take care of that in the building, since you have multiple floors and there are a lot of classrooms? How do you take care of that?
So for the indoor air quality, one thing that we had planned to do was plantation in the atrium. So we'd specified specific plants that would be planted throughout the atrium. So we have the central staircase, so the planters would be present there. So that would be taking care of some part of the indoor air quality. And the others, the spaces which are conditioned, there would be a media filter provided there. So that was what our response to the indoor air quality was.
Yeah, and in terms of the landslides, since there is slope on the terrain, but the site where we built, the area where we built, the slope was a
Mhm.
little subtle, so we didn't really have much of a risk there. Yeah.
Like I even felt like, like you're using hempcrete, which was very interesting. But even if you had left a bit of that, like a decent amount of hempcrete exposed instead of covered with an additional jali, even that could have helped with a lot of permeability in terms of, you know because it's a permeable material, so you could regulate a lot of um, air and vapor through that as well. Hempcrete, if you just plastered and not covered it with a lot of jali, because that might also be an issue later during the colder weather, like the jali, like will that help with the insulation?
Thank you, Shruti. Over to you, Aarti.
Thanks, Irma. Very well done, team. I am very happy with the materials that you have selected, the construction material, and also your energy strategies are very pragmatic. And lastly, I think you're one of the teams that conveyed to me, at least most tangibly, the volume, the scale, and the feel of the building, how it is going to look once constructed. So, very well done. A few questions and a few observations. I'm reading from my notes, so I have to look away in between. One, I'm not still not clear. What are your strategies for the north facade? There's a lot of details about what's happening on the south, which is, I think, your predominant facade, make or break the building. But I do not know what's happening on the north. And as an architect, I think you would understand that you cannot leave one facade, which actually would be the front elevation of your building, completely unattended. So that's my first question. Second is, you mentioned to Harsh also that the atrium is not being heated, and of course the building is not being cooled, and you have those terracotta jalis. Now that would be really nice in summer and even in the monsoon. But what about the cold season? How will you stop the heat transfer, like or the heat, gaining of the cold there? How will you manage that? Uh, that's my second question about the energy aspect of your building.
So for the terracotta jali, at least on the atrium, we're planning to have another glass layer with small ventilators. So they'll be like the opening and closing of them would be controlled manually. So according to the ventilation requirements. So in the summers we'll keep them open, and in the winters we'll close them.
Yeah, that's not. At least I wasn't able to make out that detail in the sections and the views that you were showing. Okay, and what's happening on the north facade?
about about the north facade, so ideally we don't have any particular facade that is directly facing the north.
Mhm.
uh, the facade that seems to be north is actually a little bit off towards the east, so we have
Mhm.
accounted for the louvers to break off the eastern morning sun, and so we have placed louvers according to those on the northern facade, and we have also incorporated planters over there and rest all is.
Okay. Yes. Also about water diagram, I think you have mentioned in the report that you'll be returning it to a public source. I mean, could be wrong. Correct me if I'm wrong. But what is your strategy for returning it to a public source? I was not able to make that out in the report.
We aren't returning the water to the public source. It's being
Mhm.
stored in the lake. The excess is being stored in the lake because it's unpredictable. So we want to have all your water supply. So we're storing it in our artificial lake, which is to the south of the site. It's not being
Okay.
returned to the public source.
Okay. Now, just two recommendations. One is about the health and well-being section. I'm still not clear what's the neutral temperature arrived at as per the adaptive model that you have used. I know you are giving the equation, but then what's the result of the equation? I think you should add that. Also, I did not see any ventilation rates, fresh air changes rate, or whatever. Those should be added to the report, ideally. Lastly, I think you are depending on using vegetation both inside the building and on the roof as a mean for controlling indoor air quality, especially indoors. Uh, I think it's just mentioning that you're going to use vegetation or plants or whatever you wish to call them as a strategy is not adequate. You must there has to be a calculation behind it. Placing one snake plant in an atrium is not going to give you clean air. I think that there's a certain quantity to it. I think that should be added to give it a scientific analogy. And lastly, about the MRF, I think it's a great idea to have MRF facility on a material recovery facility. But have you? I mean, are you aware if Kathmandu as a city has waste segregation in its sanitation plan and waste management plan? Because if the city is not segregating and you are feeding your segregated waste into the city waste stream, then there's no point in segregating outside. So have you looked at that?
Yes, ma'am. We did look at the solid waste management at a city level. So yes, they do not have a segregation as of yet, but we were thought of as a part of our scalability. We thought of introducing it so that it can be a beneficial addition to the city, because currently they're dumping their waste on the banks of River Bagmati, so which is polluting a major water source. So it will benefit both of these causes.
But then it's mute. Having one on the site is actually not. It will be an advocacy tool for waste management or zero waste, but it's actually not going to make a difference in the waste output or the actual landfill in the city, right?
So, ma'am, we're not feeding it into the waste stream of the city. We're
Mm.
selling it to
Okay.
different industries. So,
Okay.
if a yeah,
Okay.
that's
That
how we
makes.
are getting the funds. Yeah.
That makes. Thank you, team. I think Garima, that's it from my side also. Thank you so much.
Thank you, jury members. Thank you, team. Okay, so we will now take a break. We will start the next presentation at 4:30. Team variable X and jury members, please join back at 4:20. Thank you.
Fourth.
4:20. You may
Fourth.
rejoin at 4:20. We will start the next presentation at 4:30.
two, three.
Hello everyone, welcome back to the education division, and we will now continue with our presentations. Our sixth presentation is from Team Variable X. They have worked on academic block Institute of Medicine in Tribhuvan University, Kathmandu. Their project partner is Tribhuvan University, Kathmandu, Nepal. Let's do a quick AV check for our presenters. Hi Bharat, can you please turn your mic on and say something?
Yes, ma'am. Hello.
Yep, you're audible. Thank you. Hi Dhanya.
Hello.
Hi. Hi Devika.
Hello.
Hi. We're still waiting for Ishani. You have any update?
She's just coming in 1 second. Sorry.
Right. Meanwhile, you can share your presentation and put it in the slideshow mode. So, team, you will have 25 minutes to present your work to the jury. At 20 minutes, I will ring a signal which would sound like this. This will indicate that 20 minutes are completed, and you will have 5 minutes left. You won't have a 26th minute. So at 25 minutes, I'll stop you and ask you to end your presentation. After that, we will have a 15 minutes for a Q&A session. Please keep your answers direct and to the point. Uh, okay. Can you please share your screen? Yeah. And put it in the full screen mode. Yep. Okay, team. The stage is yours. All the best.
Thank you. Good afternoon, everyone. We're Team Variable X from School of Planning and Architecture, New Delhi, presenting to you Tribhuvan University's new medical super specialty academic block. Our team comprises of 10 members from third year Bachelor of Architecture and 2 members from BEM department, out of which me, Danya Gurunathan,
Devika Patil,
Bharat Kumar.
and Ashani Maurya
will be leading the presentation today. The education block is an extension of the existing Tribhuvan University campus. This building is to be constructed for 300 doctors specializing in 11 different disciplinaries over a site area of 12,000 square meter, abiding all the Kirtipur bylaws. Our site is located in the extended Tribhuvan University campus in Kirtipur district, Kathmandu, Nepal. The surrounding area is mostly residential sector. The campus is master planned in such a way that it has a trauma center, a hospital building, residential units for doctors and nurses, and academic block well connected through internal roads. The construction is done in multiple phases, and half of the site is left empty for future expansion. We analyze the site based on parameters such as land use, relief, drainage, and access, after which we primarily focused on the academic block. The institute caters to doctors who have completed their MBBS and master's degree and focuses on educating them in highly specialized disciplinaries with extravagant laboratory facilities.
Building on this site posed some tough challenges, such as passing of a high tension electric line through the site, along with a highly contoured slope, demanding design in multiple levels. The site for the academic block was too narrow and linear, and these factors highly dictated the form. The connectivity of the academic block to the hospital and the residential blocks is via the internally master planned roads. A bridge has also been designed on the floors containing the research laboratories for ease of access. We developed the form to minimize cut and fill and add an atrium, our passive strategy, and terrace gardens.
Atriums, terrace gardens, and multiple connectivity was given to enhance communication. To reduce cut and fill, we used thin floor plates and considered the natural flow of contours.
The zoning has been done carefully keeping in mind the context of the building. The library and cafe uses the contour difference efficiently to create an easy access for all users in the campus. The functions are carefully divided in terms of their public and private relationship. Ground floor comprises of the admin department and public spaces like cafe. The first floor has semi-private spaces like exam halls, computer labs. The second floor has research labs, whereas the third floor occupies lecture theaters. The high-tech biosafety level 2 laboratories are placed adjoining the corridor which directly connects the building to the hospital. An outward to inward approach was followed and the interior spaces were detailed as per the space requirements further on.
The goal of our design The goal of our design was to go beyond aesthetics. The goal of our design was to go beyond aesthetics and functionality and assist the building in its path to net zero. This academic block is envisioned to provide a comfortable environment to all its users while making the least impact on the environment, while maintaining a net zero energy and water cycle. To achieve the energy consumed had to meet the energy generated by renewable means on site. Hence, we had to reduce the consumption tremendously. This this was achieved through incorporation of passive strategies, optimizing the building envelope, daylighting, reducing the lighting power density and equipment power density, identifying the right HVAC system, and right-sizing those whose overall energy demand is compensated by a rooftop solar system. This passive system functions in the summers on the basis of stack effect and shading devices. The hot air rises and escapes, promoting the cold air to enter the occupied spaces, lowering the temperature, which is further enhanced by the ceiling fans. Thus, the cooling and fresh air exchanges are met by natural ventilation during the summer months. The CFD analysis done for the summer design week shows that the cold outdoor air enters the building through the windows, gets heated up, and then it escapes into the corridor space and is exhausted through the vents on the top of the atrium. Thus, the temperature is maintained at 28.17 degrees Celsius in the occupied areas, and the escaping air is at a temperature of 32 degrees Celsius. Similar CFD analysis was done for every floor, and the indoor air temperature inside the rooms were noticed to be ranging 28.17 to 29 degrees Celsius. The south facing atrium in the ground floor has an amicable temperature of 29 degrees Celsius, and it can be seen that the hot air rises and escapes through the vents in the topmost floor, making the air in the topmost floor of the atrium to be 32 degrees Celsius. Our passive strategy functions like a greenhouse in the winters, essentially trapping the heat and slowly radiating it into the occupied spaces. Since a space isn't naturally ventilated in the winter, a DOS system is employed to cater to the required number of air exchanges. Envelope optimization was done by optimizing the glazing, wall, and the roof envelope. A cavity wall assembly was chosen with CSEB bricks and expanded polyurethane insulation with a U value of 0.21 meter squared Kelvin per watt and a roof assembly with a U value of 0.23 meter squared kilo Kelvin per watt. And for glazing, double glazed. Um, 1 second, guys.
There's a lag in the slides.
Okay, we'll just move
It's
on to
fine.
the next. The design required a building material that was locally sourced and the earthquake resilient. CSEB bricks were chosen, which are interlocking bricks prepared by mixing and compressing sand, soil, and cement together. These bricks have greater advantages over country break bricks in terms of less embodied energy, less carbon dioxide emissions, less U value, and less cost. Since these are locally sourced, they provide employment to local community. These envelopes were simulated using Design Builder, and the reduction in the heat loss as compared to a baseline brick wall was found to be 75%. The building achieves a useful daylight elements. Ishani, do you want to take over presentation?
I'll just do that.
Sorry for the delay. The building achieves useful daylight illuminance of greater than 100 lux and less than 2000 lux for 62% of the floor area for 90% of annual hours. This optimization was done through a process. At first, the window wall ratio was set at optimum through a comparison between the heat loss and the required daylighting. The shading device was designed to reduce glare. The interior finishes were selected carefully to allow the lights to bounce. Further on, a lighting and equipment requirements were calculated for each space. Ishani?
It's still Yashashvi that's presenting with its presentation.
Lighting and equipment requirements were calculated for each space. Energy consumption was reduced by using various measures, such as shifting from computers to laptops, using appliances that have less power consumption and are Energy Star rated. The main equipment used were fans, refrigerators, laptops, and telephones. For our design, we have adapted the Indian model of adaptive comfort for mixed-use buildings. In this model, the indoor operative temperatures varies in response with the local outdoor environment. A total working hours of about 4,015 hours were taken into consideration. The dry bulb temperature and the humidity was plotted with the comfort band in place and the uncomfortable hours were identified. 52.6% of the time, the temperatures were lower than the comfort temperatures, and 23.4% of the hours were experiencing higher humidity levels. By adapting the passive strategies that we adopted, we were able to achieve comfort for 83% of the hours, which is 3,335% of the 35 hours. And there were 14 hours that were still lying below the comfort band and 25 hours that they were lying above. The summer months are using natural ventilation, and the ceiling fans can bring down the temperature up to 2 to 3 degrees Celsius. In summary, in the summer months, the passive strategy alone, with the help of natural ventilation and ceiling fans, can cater to the local environment. And in winters, a DOS system was used only for fresh air exchanges. Coming to the right sizing of the DOS system, the ventilation rates were calculated space-wise for each floor using NBC standards and the formulas given by the Solar Decathlon India. On calculating the rates for each floor, the right size systems were then assigned AHUs as per the sizing requirements. So we first optimized the LPD and the EPD, and then we added our passive strategy which helped lower our EPI. We reduced the HVAC loads by optimizing the envelope by reducing the heat loss. By these measures, our EPI came down to about 10 kilowatt hour per square meter per year. However, our passive strategy did not allow any fresh air exchanges in the winter months, and hence we had to add a DOS system for fresh air exchanges. So this DOS system only functions during the winters and throughout the year in the laboratory, which also has an extra filtration tuner to it, which increased the volume and also increased our EPI to about 35.3 kilowatt per square meter per year, kilowatt hour per square meter per year. A series of simulations were carried out to attain a EPI of 35.3 kilowatt hour per square meter per year, which is 74.7% lower than the base EPI, which is 100 kilowatt hour per square meter per year. The entire energy consumption of the building is met by the energy generation by the PV panels. A plant of 320 kilowatt size consisting of 825 panels is planned across the rooftop of the academic block, the connected auditorium, and the academic block's parking. And with this system, a total energy of around 4,96,000 is harnessed annually.
The daily water demand of a building is kept at 31.5 liters per capita per day. With the use of low flow fixtures, we have managed to reduce the indoor water demand by 54%. Through drip irrigation, planting native trees, and xeriscaping, we have achieved a 42% reduction in the outdoor water demand. Rainwater being our primary water source, it accounts for 56% of our water demand. Annually, we are letting out 562 kiloliters of water to the public source. We are proposing an integrated wastewater treatment system in which a three-chambered septic tank is connected to the SPT system for combined treatment of grey and black water. Our primary source of water is the rain. Our site had a potential of harvesting 57 lakh liters of rainwater, out of which we are letting out 12 lakh liters as stormwater discharge into bioswales, recharge wells, and check dams. Rainwater being our primary source of water, we are also drawing water from the municipality. Collected rainwater is stored in the underground tank, and the municipal water is stored in a separate underground tank, from where they both will be pumped to the overhead tank. From the overhead tank, they flow to reach various utilities of the building. Water from the WC, urinals, vedettes, and kitchens are considered as black water and are directed into the three-chambered septic tank, in which the third chamber is the filtration chamber, which stores the effluent of the solid waste. Water from the laboratory faucets, cleaner sink, showers are considered as grey water and are directed to the SPT system along with the effluent stored in the septic tank. From the SPT system, the treated wastewater is pumped to the flushers of the WC for their reuse and can be used for irrigation. Wastewater from the laboratory faucets are slightly acidic in nature, hence they are neutralized with lime in a separate lime tank. We are proposing an integrated system for wastewater treatment. The grey water is directly sent to the SPT system for treatment, and the black water is first sent to the septic tank, in which the sedimentation happens in the first two chambers, and the effluent gets separated out in the filtration chamber, from where it will be pumped to the SPT system for treatment. So this is a site plan showing the placement of recharge wells, check dam, bioswales, and xeriscape planning. Now moving on to solid waste management. Waste collected from different bins are sent for manual sorting. Only biomedical waste skip this process and directly reaches the incinerator. Food waste is decomposed through large machines called ecobots. The collected leaf waste is decomposed through vermicomposting. Finally, the decomposed food and leaf waste are sold as compost in the market. Plastic, paper, and cardboard waste are further segregated in a material recovery facility and are sold in their respective recycling market. The money generated out of selling these recycled waste can be utilized for infrastructural development of the campus.
Our innovations provide solutions for problems faced not only by our building, but ones that can be scaled and used throughout Kathmandu. They include recycling plastic waste into bricks that cut down heat loss to the ground, a cheap and easily scalable kinetic facade using locally available materials, reusing excess heat from ice-lined refrigerators, solar concentrators to provide hot water in times of distress, social distancing panels to slow down the spread of infections, and ceiling mounted phase change material in rooms with high occupancy. One of the major constraints of our building faced was heat loss through the walls in the ground floor and the basement. To combat this, we have designed a wall section using plastic bricks and additional insulation from the library books and air gap. Plastic waste like gloves, containers, and syringes produced during the phase-wise construction of the campus will be utilized to make the plastic bricks. Tribhuvan University's construction is planned out in stages with the hospital and other blocks constructed before the educational block. Utilizing this time gap, Plastic waste generated on site during construction and running of the hospital block is collected and stored. This waste is shredded before going to the compressing machine. The compressing machine melts the shredded plastic with superheated water, and by compressing in a die, the plastic block is created. The plastic blocks are stacked and rebar is added while assembling. The section consists of a layer of plastic bricks reinforced with rebar, followed by an air gap and a layer of books. Using waste plastic cuts down the amount of non-biodegradables entering the environment while also cutting down heating loads by preventing heat loss through the ground. To follow Kathmandu's varying need for shading, we designed a facade with a changeable window-to-wall ratio. Using cheap and locally available materials and a simple mechanism that can be easily replicated ensures that this facade can be scaled to fit any building, old or new. Each unit consists of a simple fan that opens up to cover a portion of the glazing. They can be individually adjusted to provide more shading in the summers and less in the winters. With temperatures going up due to global warming and unpredictable weather in the future, these units provide a cheap and sustainable solution.
Expansion joints at regular intervals of 30 meter is being introduced to allow movement during earthquake for flexibility due to thermal or seismic activity. Instead of a standard vertical pile foundation, an inclined pile foundation increases the structure's horizontal stiffness, resulting in a shorter natural period corresponding to a global bending vibrations of the structures. And this decrease is likely to increase the superstructure seismic response. Our building is designed as per the fire safety norms of NBC Part 4 by using Type 1 construction, which provides a fire rating of 2 hours. 3 cores are designed and constructed at a maximum distance of 45 meters with pressurization shaft and firehouse cabinets. Every livable space in the building is equipped with fire extinguishers and a fire water sprinkler system. A 6-meter wide fire tender road runs around the building's perimeter, allowing a fire tender's access from all sides. Next slide. The building is divided into 2 blocks, with Block A attached to the hospital and Block B independent from the hospital. Both blocks have their power supplies as well as the separate core. In case of a virus outbreak, Block B can be repurposed to accommodate those who are unaffected, while treatment can be administered in the Block A. Also, the block can share the load due to 3-phase system and help achieve sufficiency in case of a system failure in any of the blocks. On normal days, the cafe tables can accommodate 4 to 6 people, but in the event of a disaster, it may be converted into a twin-sized bed by adjusting the table height and folding the backrest of the sofa seat. The front of the table has a backrest for a seat in front of it, giving students a little bit more comfort. These tables can be converted into a bed during an emergency by stacking them side by side and placing a mattress over them. Within our building, we plan to store roughly 29,000 survival emergency tents that can be used in and around site in the event of crisis. The survival emergency tent can accommodate 2 person, water and wind resistant survival tent that can be withstand severe rainfall, strong winds, snow, and freezing temperature, and can be set up quickly and effectively within seconds. Global warming and climate change are one of the most unpredictable hazards that is fast approaching us. We wanted our design to adapt to seasonal change while still catering to the required levels of thermal and visual comfort. We have tackled this with kinetic facade that can be manually controlled by pulling chains to allow rotation. The window wall ratio can be adjusted to allow or let go of heat as and when required. The rotation of the facade members can go from the window wall ratio 20 to 100 as and when required to impact the heat gain due to glazing. In our design, we aim to make it user-friendly for all groups of people, including the physically disabled people. The design of spaces is inclusive, accessible, informative, and flexible for every user. For non-ambulatory and semi-ambulatory people, a ramp with a 1:10 slope has been built at the building entrance. To assist blind people, guiding blocks are placed both outside paths and within corridors inside. Doorways are provided as per the disabled accessibility standards. PWD toilets for disabled people are provided on each floor. Wheelchair accessible lifts are being provided on each floor.
A building management system has been installed in the building to manage and monitor equipment such as air conditioning, heating, ventilation, lighting, etc. by collecting data through the network of sensors, installed equipment, and third party integrated systems. A management app has been built for staff to report problems and collaborate with various departments for maintenance. The user flow of the app depicts how a central server gets data from sensors, equipment, and human data points, which is processed into final output. An art installation has been centrally placed in the building, which uses real time data from the BMS system to display the energy patterns. Whenever the light shine outwards, the energy is being generated, whereas when they shine inwards, it is being consumed. The total project estimate is about 71.1 crores, which is about 48,400 INR per square meter. This cost is 5% less than the allotted budget by client. In terms of cost breakdown, civil works and MEP services took up major part of the hard cost. The decision of incorporating a DOS system instead of a standard VRF system helped us reduce the capital cost significantly by 96%. However, there was an increase in the expenditure due to use of CICB bricks, glass curtain wall, and kinetic facade. The life cycle cost analysis of the solar PV system shows that we are saving around 37 lakhs INR per year and the payback period will be 3.5 years. And the LCC of the proposed HVAC system shows that we are saving around 22 lakhs INR per year with a payback period of 4.72 years. We have also installed CICB brick making machines to reduce the cost per brick by doing on-site brick production. We plan to recover the initial capex of the machines by saving them from difference in cost of market bricks and in situ bricks. Further on, these machines will be available for local families to maintain and continue the production of bricks for sale as a part of social empowerment. Concluding the presentation, we would like to thank our faculty, project partners, and industry partners for encouraging us throughout the project, and Solar Decathlon India for providing us with the opportunity and resources for us to come up with this project. We Variable X aspire to better the community with one sustainable building at a time. Thank you all.
Thank you, Team Variable X, for that insightful presentation. Let's hear the jury's comments and take questions from them. Aarti, shall we start with you?
Thank you, Garima. So, congratulations, Team Variable X. One of the most beautiful reports in the group that I have been through, and the presentation is equally appealing also. So, congratulations on that. Couple of questions and then maybe a few observations. I don't think you have shown any plans in the presentation, but can you tell me what's your strategy for daylight in the library? It seems to be in the basement.
So the in the library, actually, the services are facing the north side. The north side is essentially the part where the contours block the light. So our library is placed like a lower basement level. So it's completely open towards the southern side, and the north side is completely closed by the earth. And a lot of the reading areas are placed towards the southern side and have that facade, which you can change according to the daylight requirement and the heat on the southern side. So daylighting in the library should not be an issue because a lot of spaces like our other services, AHU rooms are placed towards the northern side to utilize that area.
So it is not essentially a basement, but accommodated in the contour difference.
I recommend that you look at your plans and sections again. It suggests that your library doesn't have any daylight. Just go and tally them. Uh, Now, coming to the energy strategy, you have, I think, eliminated heating altogether, right? Any active heating or cooling. I did not see any calculations, any heat transfer calculations, or any simulation suggesting that thermal comfort conditions have been maintained there. Is that correct? Were there some things have I missed something? Because you are saying that it will be comfortable, but I have not seen anything which suggests that it's actually going to be comfortable without any heating or cooling.
So we had run an annual simulation in Design Builder, an early annual simulation. So from that simulation, we had taken the temperatures, indoor operative temperatures, and then we had plotted the comfort graph, which should we bring up the presentation again?
Yes, please. I think it's a good point. Please show us this slide.
Yeah. Maybe I can only share it. Yeah. Can you go up to the comfort graphs? I think it's slide 26. 26, yeah. So in this graphs, the hours and the temperature plotted for this. So this we essentially took, so there are 4015 hours in this. So the first one was taken from the EPW file data, and the second graph, that is this graph is essentially, yeah. Can you put it in full screen?
This is from which software?
So the Design Builder gives you a tabulated form of the hours and the indoor operative temperature and humidity. So this is essentially from that tabulated data. So we thought visualizing it in this way would be better for us to explain. We could,
and which this would be is this like a general graph, or is it for a particular space in that project?
for this we took one specified space. So this was our lecture theaters, the inside temperature of our lecture theaters.
So you're saying that 65.3 were comfortable and 20.8 had high humidity.
They're still in comfort temperature, but they have slightly higher humidity. Yeah.
Aarti, do you mind if I add to your question?
Please do.
Because
let's not keep a formal structure.
I was also thinking about this point. So just to understand, right? I mean, I think because it's the crux of your kind of building, right? The major statement you are saying is we don't need a system to manage this building. We're going to rely totally on the architecture passive strategy. So there are two dots. I mean, color differencing is a bit difficult, but the darker green essentially is naturally ventilated. And it means what? This is climate data, or this is also being predicted by are these two different type of spaces?
So these are the same spaces, but we plotted it this way because in the summer months, so the dots that are in green color are essentially the hours that are in the summer months and in the monsoon months. So essentially, we're primarily just using natural ventilation for these months. But in the winter months, we had to rely on a fresh air exchange because air infiltration will bring our temperature, indoor operative temperature, below again. So for that spaces, so for that hours in the winter months, we've essentially depended on a DOS system for the fresh air exchange. So in that, we have a heating coil which heats up the exterior air and then supplies it to our space.
Right. So what I read from this is essentially that when you use your system, your humidity levels fall within the comfort band, right? And all the rest of the green beds are above 70%. So the humidity is not managed in your building. It is not comfortable.
So there are two reasons for that. One is that the period that we're mechanically ventilating is essentially winter, and the humidity levels in winter in Kathmandu itself does not go higher. And
No, I am just reading your graph, Dhanya. Your graph says that there are lots of dots up to 20%, maybe 21%, essentially, which are above, 65 threshold that you have kept, right? That is one of your comfort criterias, isn't it? Dry bulb you are able to meet because of moving it, and so there is a chunk, big chunk which is humid, right? Essentially, you cannot, above 80%. It's really, it doesn't work out. You will feel uncomfortable because of something. Now, that said, do you do anything after this chart to correct it? That's what I want to know. This is showing a problem, a decently big one, right? Because I agree with you. See, I'm always on the side of passive architecture succeeding, but the real fact is that if comfort is not provided, people will install some kind of AC very soon, right? So we want to avoid that. So how do you resolve this? Do you really do take some action on this simulation later in your design?
Ishani, do you want to take this? I think she'll be able to
Yeah.
better explain.
Sure. Take your time. We do feel it's an important bit, so please
Yeah.
take your time and
We can
answer
move
it.
to other questions also in the meantime if you need time to answer them.
Yeah, I just wanted to add to what Danya was saying earlier. So, since the the part of the year which has humidity levels which are higher, they are mostly naturally ventilated. So that's why we thought that, and also since it is a educational building, so we thought that some sort of adaptive comfort would be a better situation for school students, because they are not only going to reside in that very building for a longer period of time, but also might move to other parts of the world. So adaptive comfort was one reason for that. And the second was that also because there is natural ventilation and not mechanical ventilation happening during that time. And besides that, we did think of adding dehumidifiers. We did consider adding dehumidifiers to our loop, but then due to the broad reason was the adaptive comfort, since it's a school, it's a university setting. So that is why we refrained from adding energy due to that.
Generally, the adaptive model is really talked about in terms of dry bulb. Conceptually, I can say yes, if you are outside, you want to accept higher levels of humidity, but these are spaces where you're inside. Probably some of them are teaching spaces, right? So that's why I'm having difficulty accepting stuff above 80%, right? Especially it is just too much, but that's okay. Let's move to the
Uh,
next point.
one
I'll leave
more
it to
thing.
our. Oh yeah, please go ahead, please.
Yeah, so one more thing we had to add to this is a super specialty academic block that we're designing for. So when we talked to the client, what they essentially told us was we don't necessarily need anything in just talking, because we're not aware of Nepal's climate primarily. So we were just talking to the client and they were saying we don't necessarily require cooling and all, but heating we might need. And they also mentioned that they only stay in the lecture theaters for 2 hours in the morning. But when we calculated, we took the entire time of the day because the building is operating entirely. But their lectures usually span from 9 to 11, and then they shift to the hospital block. While some of the other functions might be happening, the students necessarily just go back and forth to the hospital and come back. So we necessarily thought adding a dehumidifier for those, which is essentially going to be operated for those 2 hours, would rather take our energy
Do you
consumption.
do you think do you think the college will take a decision that no classes will happen in the afternoons, or late late
So,
late afternoons when humidity is
so
high?
no, that's not the reason, but their schedule. So these super specialties doctors' schedules. So they have this. From what we understood is they work at the hospital in shifts, and their lectures, which are more like case discussions, would usually happen in the morning when the attending.
Personally, I can accept your logic, but for a building, to have some resilience that somebody decides that for the coming semester, my classes are going to happen 3 o'clock or 4 o'clock in the afternoon. I would not be able to change that decision. So got your point. I think, but that then what you should have done was you should have actually taken this graph and produced another one and said, okay, by the way, we have a confirmation from the client. Most of these classes will happen here, and yeah, all the humidity levels fall down. They are essentially not the period where we are going to use it. But that's not what you say, right? So I'm not able to take that.
Okay,
Okay.
that's a mistake on our part, but we will look into how to dehumidify the space as well.
Yes, it's not that going to be that big a move, right? And yeah, you should think about it.
Yeah, so couple of just I'll stretch it once more. Is that I believe that I'm not looked again into this space function program, but it seems you would have some labs where there would be equipment. So probably there would be a need for some kind of space temperature controls there, right, Ganya? Do you have labs in this building? I assume there are some labs. I remember writing
Yes,
some.
so we have research laboratories, and so we've done biosafety level 2 research laboratories. So we have provided our filtrations, which was the requirement, and the requirement for temperature control was specifically to their specimen collections areas. So it could either be a walk-in chiller room where the specimens could be kept so that there's no spoilage, or it could be ILRs. So we have made the move to go with ice-line refrigerators, which maintain temperatures at 2 degrees Celsius and have a power backup of about 24 hours. 24 hours, yeah.
My last question, I think I'll leave it because I think I've taken too much time there. You mentioned that you have a BMS system. Now, why have a BMS system when the only active system that you have is the DOS, which most likely comes with its own inbuilt or some smaller attachable control and monitoring unit? Why have it? You're not going to be able to control much with a BMS unless it's what's happening with your wastewater and water treatment, and also to some extent the DOS system, which again said it's possible to have a smaller, a mini BMS system for your DOS. Why have a whole building BMS? EMS works best when you have a lot of active systems, building systems, and capturing what's happening with them. Is your chilled water, or is your heated water, or is your steam temperature or hot water temperature? Is it delivering at the right temperature? Diagnostics of that sort. You don't have much of it in the building, so I have a BMS.
Uh, yeah, so one another thing along with BMS that we had was a management app that we thought about. So we thought that besides the internal problems that the BMS system might tell us, we can integrate the external problems as well in that system itself, so that both of these problems can be managed simultaneously. So that was one major reason. And yeah, and using the BMS system, we also wanted to make the educational building socially conscious, and using that installation that takes up data from the BMS system. We also wanted to tell the people residing in that building how the system is actually working at that point of time.
Okay. Thank you, Shani. I think that's from my side. I'll hand over to my colleagues. Thank you.
Thank you, Aarti. Thank you. Shruti, any comments and questions from your end for the team, please?
Sure. Thank you. Thanks, Garima. Thank you for that presentation. It was very cohesive, and I think one of the best presentation in terms of your strategy of communicating everything. My main comment has, I think, been addressed by both the jury before around passive strategy. Just one comment that I would add to it is that you mentioned that the optimum temperature that you believe that should be there is between 28 to 29 degrees. I would just like you to look if that's the optimum for the entire building. Like there might be rooms, there might be spaces in the building where that's not the optimum for the right comfort that the students or other people in the building would look at. Besides that being a standard. Secondly, besides passive strategy, because that's been discussed, I think your cost of construction is slightly high per square meter that you have. So I would just like to understand, have you done any sort of calculations around the breakdown that you're looking at that you can pass on to the end user who's constructing it? Like when would they look at the break even? And also because you're using things like plastic bricks, around scaling it, is there enough plastic available around that area, or in the amount that is generated that you can make enough bricks for construction? So around affordability, plastic bricks would be my two additional comments besides passive strategy.
Okay. So, answering to the first question was asked about the optimum temperature. So, the comfort band or the optimum temperature is not 28 to 29, but instead it's the summer design peak. The summer design peak temperature, we're achieving an indoor operative temperature that was 28.17 degrees Celsius according to our CFD slices. So even at the maximum temperature, that is what we're achieving, because the outdoor climate is also not that harsh. So that was that, and I think plastic bricks Ishani will take on.
Besides that,
Actually, we
also,
are running out of time.
I have
So,
one important question. Garima, please allow me
sure.
after they answer Shriti's question. Just, I'll be very quick about it. Yeah, go
Yeah,
ahead.
please
I mean,
continue. Please continue answering the question.
okay. So,
okay,
may I?
go
Yeah,
ahead. Go ahead.
Ishani.
Go
Ishani,
ahead.
please go ahead.
So, about the cost of construction, this is a government-funded project. So, the budget constraint wasn't that high. So, the amount will be given by the government in loans, and we will be using it as per that. So, that is the thing. And, yeah.
Ishani, the waste, the plastic.
Harsh, do you have a question or shall we
Yes.
conclude?
Okay, I think just very quickly. See, when I was looking at your report, guys, I wanted this answer. At portions of your report, your site area is, about 8,500 or less square meters is mentioned, right? But when you start looking at PV, your site area is mentioned as 12,000 something, right? 12,500. So what I concluded is that one of your solar arrays is actually not in your site. So is my understanding correct? The one on the north, you have three arrays. There is one extremely on the north, and I think that is really not on your site. Could you react to that?
Yeah.
That's my
So the
conclusion from your drawings.
Yeah, so that is essentially the academics car block, but they have a multi-story car block that for academic students as well, for the students, faculty, and all. So we essentially, since our building was very slender, we didn't want to use the entire roof area. We opted to use some of the parking's rooftop area.
Okay, so it is out of your site. Okay, all right, fair enough.
It's
But
still within our campus, but out of the academic site. Yes.
right, I mean, yes, I mean, I am not opposed to that idea, except that I was looking to evaluate it, in terms of net zero on your site, right?
Yes.
While you could have easily said in the report that you want to actually use certain areas of the campus, which has not been kind of conveyed. That's the whole thing, right? So no strict opposition to that. Just thinking how to look at this. All right, let's go ahead. Thank you very much, guys. A very interesting discussion.
Thank you, team. Thank you so much.
Thank you, jury
Thank you, ma'am.
members. Thank you, team. Let us take a minute before we start the next presentation. Our next presentation is from Team Venturis. They have worked on SPKM School and Junior College in Navi Mumbai. Their project partner is Sri Vile Pale Kelavani Mandal. Let's do a quick AV check for our presenters. Hi, Varshil. Can you turn your mic on and say
Hello.
something? Hi.
Hello. How
Hi,
are you?
Mihika. Hi. Hi, Anish.
Hi, ma'am. How are you?
I'm good. Thank you. Hi, Yug.
Hi.
Okay. You can start sharing your screen with the slideshow mode on. Yes. So, team, you will be having 25 minutes to present your work to the jury. At 20 minutes, I will ring a signal which would sound like this. You won't have a 26th minute, which means at 25 minutes, I will ask you to stop and end your presentation. After that, we will have a 15 minutes for a Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best.
Thank you. Good evening, everyone. We are Team Venturis. I'm Varshil. We have with us Anish, Mihika, and Yug, and we'll be presenting our proposal as a part of the Educational Division of Solar Decathlon India 21-22. Our team comprises of 15 members, 12 being fourth-year B.Art students from Balwant Sheth School of Architecture, and 3 fourth-year instrumentation engineers from Vivekananda Education Society's Institution of Technology. Our team used a feedback loop as a part of the process. Only after extensive data collection and comparison, input from simulations and discussions, and previous and frequent back and forth between conclusions from previous stages did each stage proceed.
Partnering up with SVKM, objective was to design an ICSE school located in Sector 34 of Kharghar, Navi Mumbai. The school would be attended by about 2,800 people, including students and staff, and would function from 8 a.m. to 5 p.m. The site is located in a region with a tropical warm and humid climate, and the height restriction for the area is 30 meters according to the UDCPR. The immediate context of the site included residential zones to the east, west, and north, and a proposed corporate park to the southwest, which is currently barren, and an upcoming football stadium accompanied by practice grounds in the recreational zone to the south. As per the UDCPR, the total permissible built-up area is 10,408 square meters, with a ground coverage of about 40%. Her main challenges came from the immediate context of the site. Abutting the main road and the proposed recreational sector of Kharghar, the site is susceptible to noise. There is inconsistent water and electric supply, along with a high groundwater table on site. Some of the strengths include that since the neighborhood is a fast developing area with high investments, it acts as a major attractor point, and the absence of any ICSE schools in the context is also an added factor.
We started off by simulating the radiation analysis as well as the shadow range analysis of the site with the surrounding context. Radiation and shadow range analysis was done in order to understand the intensity of radiation and the various areas of the site receive and shadows that would be cast on the site. Overlaying the results onto the sun chart, we obtained adequate data to devise the various efficient shading systems. Due to the presence of the building on the east side, not much shading was required on the eastern facade. Monsoon overcast would be a problem in the north and east, therefore, proper daylight on the north and east facade was required to be incorporated. Buildings in the north did not cast any shadow, and hence that could be neglected. Critically studying the IMAC model for comfort on an hourly basis, we listed down key observations. Based on our findings, we revised the chart and stratified it based on 3 categories: below comfort range, above comfort range, and comfortable range as shown. We learned that 43% of the total hours in a year lie in the uncomfortable range. To study the comfort requirements based on the working hours of a school, we cropped the time period from 8 a.m. to 4 p.m. Here, 61.5% of the hours lie in the uncomfortable range, as shown in the pie chart, and need some external cooling system to attain comfort. We then tried to look at the winds prevalent in Navi Mumbai and hence simulated the site in order to carry out the wind analysis and to obtain the windrows diagrams for 3 months consecutively. We then looked at various wind directions and patterns that are formed during the course of the year. We then applied relevant strategies from these observations and data within our structure. To begin our design process, we opted to use a micro to macro strategy, optimizing the smallest classroom module first, then constructing a larger, more efficient module. An iterative process using eight shading strategies and 3 different wall-to-window ratios on the long and short walls were conducted in order to discern the most efficient and optimized module with low EUI and high applicability.
Thus, what was achieved was a classroom module of 6.5 meters by 8 meters with an area of 52 square meters in accordance with ICSE norms that has a window on the northern and eastern facade, agrocrete as the wall system, and a 3-meter wide corridor on the southern and the western sides, which provides shading and the necessary noise buffers. The north and east facing windows have a chhajja of 750 mm located at 2900 mm. According to the chosen WWR, that is 40, simulations for the illuminance, spatial daylight autonomy, and glare were done for 3 different iterations of the classroom. That are classrooms that face the south without any shading devices, classrooms that have shading devices, and lastly, classrooms with north facing windows with a corridor. For the first iteration, due to the absence of any shading devices, most of the area of the classroom is illuminated, exposed to intense daylight, and lastly, experiences a large amount of glare. For the second iteration, due to the presence of shading devices, the intensity of the illumination, spatial daylight autonomy, and glare are reduced in comparison with the first iteration. This indicates that the presence of a shading device can drastically reduce the heat gained within the classroom. For the third iteration, due to the presence of the buffer space on the southern side of the classroom and the windows on the northern side, the corridor is exposed to most of the daylight and thus illuminated and experiences most of the glare while the classroom receives the diffused northern light, which is not that intense. This keeps the classroom comparatively cooler while still being exposed to sufficient daylight and being illuminated sufficiently with much less glare. A DC system, size of 196 kilowatts, provided on the terrace generates a total solar power potential of 320,500 kilowatt hours per annum. With an array tilt of 20 degrees and an azimuth of 180 degrees, the net generation is more than the annual consumption of the school, which is 280,500 kilowatt hours per annum, making it a net positive energy building. The respective bar graph indicates the reduction of the EPI after inputting the data and the various strategies that were incorporated, such as considering only those hours out of the operational hours that required external cooling in order to reduce the overall HVAC load, incorporating sensor-based lighting systems, and lastly, altering the openings for efficiency.
Looking at the water performance, we aim to reduce the water demand per person first and thus lower the demand for the whole structure. Taking 45 liters per day per person as per NBC, we achieved a reduction of almost 60% by using low flow fixtures, harvesting rainwater, and treating and reusing grey and black water. The diagram on the left shows the reduced water demand, dividing the 18.3 liters per person into the multiple areas where the water is used. Rainwater was harvested from various surfaces including hardscape, courtyard and landscape areas, as well as vertical surfaces. The water from the municipal supply is used for various purposes like the HVAC, cleaning and washing, which produces grey water, and drinking, flushing and cooking, which produce black water. Both grey and black water were then taken to the Eco STP for treatment, after which they are used for flushing, irrigation, and other functions. Similarly, rainwater is harvested, filtered, and reused. The system proposed for the treatment of water is the Eco-STP system, which compared to a conventional system requires no electricity to run. It is an underground system with a low maintenance cost since sludge removal is done once in 2 to 4 years. For the treatment process, the wastewater is redirected to the system and it goes through a 3-stage Rumen digester filter, charcoal and sand filter, and an ozonizer. And after treatment, it is stored in a collection tank to be used later for flushing, irrigation, and other purposes. Any excess treated water is sold to the public domain or returned to source. Thus, the reduced annual water demand is 15,075 kiloliters, with 13,379 kiloliters of water being treated and reused, and about 12,500 kiloliters of water is harvested. Thus, about 10,800 kiloliters of water remains as an excess, part of which is stored as surplus to be used in case of emergencies, and the rest is either returned to source or sold for revenue.
Resilience has been approached at 5 levels: seismic resilience, fire resilience, flood resilience, community resilience, and water and power backup. As an overview of the strategies, this diagram shows the use of solar PV cells, low flow fixtures, flexible and adaptable spaces, rainwater harvesting, and emergency systems. Quantifying it, it was concluded that the total water storage capacity is equivalent to 6 days of the daily water demand, while the daily solar power generation is also higher than the daily electricity consumption. Structural design is in accordance with seismic zone 3 requirements and codes, along with the right sizing and removal of any redundancies to strengthen its resilience against earthquakes. An already high groundwater table increases the risk of flooding and damage to the structure. Along with stormwater drains and efficient drainage systems on terraces and courtyards, an additional level of protection has been provided in the basement to reduce any damage. Each floor has been provided with smoke detectors, sprinklers, hose reels, fire alarms, and fire staircases for smooth evacuation. The basement has also been provided with heat detectors and water or sand buckets. A 6-meter wide offset has been provided on all sides of the building for access, along with site hydrants every 30 meters. Each room may easily be converted into a relief center with enough open areas as part of the community's resilience. On the first level, the multipurpose hall may be turned into a community kitchen. Classroom and lab sizes were also set to multiples of the basic classroom module, allowing for easy functional changes. The structural design has also been optimized to allow future expansion.
Costing is the most important aspect of any proposal. Overall cost reduction can be achieved by value engineering, construction technology, and efficient project management. Cost is proportional to the major loads incident on the building. Thus, an attempt was made to decrease the loads at a primary level by incorporating meticulous, innovative passive design strategies. Cladding materials were altered, and cost-effective materials such as bamboo and cinder blocks were used, resulting in an efficient facade system that decreased the overall capex. HVAC systems present in all buildings contribute to a major percentage of the cost, both capital expense, which is almost 20% of the hard costs, and operational expense. Keeping the overall cost in mind, an air-cooled variable refrigerant flow system with treated fresh air AHU system along with a hybrid solar controller was selected to decrease the overall loads on the building. This would in turn reduce the OPEX by 17.8%. Right sizing of elements saved 20% by volume and 32.8% of the civil costs. To achieve optimum sustainability in practical sense, it is crucial to consider the fixture cost and its energy requirements and achieve a balance between them. Therefore, we surveyed multiple products available for various lighting fixtures and shortlisted 3 options to compare with the base case and suggest alternatives to it based on cost, LPD, wattage, etc. as given. Bathroom fixtures that optimize the usage of water were selected. To this, the operational cost, that is water consumption per annum, was cumulatively added. It was observed that in a 5-year cycle, there was a significant decrease in the OPEX compared to the base case. Physical properties of a variety of materials were studied, and the most optimum one was selected for application in different building systems to achieve an efficient, sustainable building, not only in terms of cost, or not only in terms of energy, but also cost. A tentative life cycle cost mapping of the building was done, and it was observed that the total cost incurred by the building will be equal to the revenue generated by the institution in 5.3 years. If additional streams of income generation like urban farm produce selling, leasing out of the multipurpose hall, and workshops during weekends were to be considered as income streams, the total cost can be recovered in 4.5 years.
Our approach to innovation was to make something that is conventionally difficult to maintain and replace into something that could be incorporated into the curriculum, allowing students to develop soft skills along with the community. The primary goal of this facade was to function as a noise buffer, minimize heat gain, and purify the air owing to nearby industries. The facade module is made up of 2 parts: the lower cinder blocks with plants and movable bamboo fins. The green facade has been split up into two parts, the internal and the external planter wall. The external planter wall has a mix of air purifying plants, flowering plants, and herbs, while the inner planter wall has only flowering plants and herbs. The plants thus harvested could be either sold to the public or made part of the curriculum itself. Additionally, the terrace gardens would have a larger mix of butterfly attracting plants to increase the biodiversity of the area. The rotatable fins have the ability to lower the incident radiation and create more comfortable corridor spaces. The diagrams here show the possible angles of rotation and the corresponding annual average lux for each position. The large voids on the southwest and northeast have large operable blinds to easily adapt the space into outdoor classrooms. A magnetic layer placed between the two corkwood sheets magnetizes the blind while also allowing material to be pinned to it, making it interactive for pupils. Enjoyable and interactive spaces are created by the light play due to the acrylic sheet inserts made from recycled plastic. Lastly, to instill the idea of a circular economy from a young age, several furniture pieces in common and breakout areas would be made from reclaimed or construction waste, including urban farming trenches, bamboo seating and creeper walls, and paint bucket storage options. Additionally, to make it a part of everyday learning, constant segregation and collection of paper and plastic to recycle in partnership with an NGO is proposed.
The perspective section, cut along the north-south direction, shows the various temperatures or the wind flow on various levels of the building. The bottom three north-facing sections illustrate the amount of radiation incident on the structure during the three extreme periods of the year. As part of the requirements, all classrooms will have two air conditioning units. The classrooms have been designed such that they are moderately comfortable with natural ventilation and reduced radiation, even when the air conditioning system is not in use. Various ducting layout iterations have been done with the goal of achieving efficient air changes in the zones. In the classrooms, we maintain 5 ACH, meeting and exceeding ASHRAE standards for the same. To create a stable structural system while reducing the overall cost, we used the method of right sizing the elements, which helped us to create an efficient structural system which resists lateral and gravitational loads while transferring the loads from all spaces without deformation. It also helps to reduce beam depths in order to maximize headroom, incorporate all services including HVAC and plumbing, and create an earthquake resistant structure and minimize the damage to the structure.
All the systems within the structure, like the HVAC, fire safety, security, and lighting systems, are integrated within one building management system. The HVAC and lighting systems are sensor based systems and would be regulated based on the occupancy of the rooms. This helps to reduce the overall electricity loads of the structure. The fire safety system consists of a fire alarm control panel connecting multiple fire alarms and smoke and heat detectors, which would be activated in case of an emergency. Similarly, the security and access control panel detects the ingress and egress of the people, and security cameras ensure a safe environment. One of the goals, along with creating a net zero building, was to create awareness amongst the users. In order to achieve this, we have proposed an app that will be projected on screens all around the school. This allows the students and faculty to look at the real-time energy consumption as well as other components like waste recycling, urban farming, and water consumption. This promotes healthy competition within the student divisions where they are rewarded for their efforts in reducing energy consumption or collecting waste to be recycled.
Once the classroom module was optimized, it was multiplied and scaled proportionally to form the base blocks based on requirements and areas. A conceptual section through the building shows the placement of the various programs, including classrooms for all grades, labs, and a library. As a part of the brief provided by the project partner, attention had to be paid to reduce intermingling of multiple batches within each other while still promoting self learning. A requirement matrix based on functions, daylight, ventilation, privacy, and glare was made to further detail out relative positions and interrelations. As mentioned before, this entire process has been heavily iterative with constant feedback and discussions with the project partner. The four iterations below include multiple courtyard positions and shapes as well as varied placement of base blocks. The process of massing provided us with a framework for placing functions to tackle our main site issues, that are noise and solar heat gain. From a mass equal to the permissible ground coverage, a void was created for the courtyard, allowing for natural ventilation and stack effect. Keeping the natural flow of wind at the site in mind, strategic double volume voids were placed at opposite corners of the mass. The service cores have been shifted to the northwest and southeast to allow for unhindered connectivity, both in the physical and visual realm. Finally, the planned green facade was applied as skin to counteract the most susceptible faces, that are the south and the west.
Our initial iterations included the corridors placed along the courtyard with the classrooms along the exposed facades, which led to a high amount of solar heat gain. Thus, to minimize the solar heat gain, the south and the west facing classrooms were shifted inwards and the corridors were shifted towards the external facade. Kinetic bamboo fence, along with vegetated cinder blocks placed along the corridor, optimized daylighting and comfort requirements. A shadow analysis was conducted along the north-south section of the structure for 3 different days in the year in an attempt to comprehend and determine the efficiency of the courtyard. An annual radiation analysis of the structure was also done to understand the varying amounts of radiation the various parts of the structure were subjected to. To understand the experiential quality of the spaces within the structure, we've taken a few internal views of the same. The top left image shows a view of the internal courtyard seen from the upper floors, and the bottom right image shows the view of the innovative jali incorporated within the space created by the double-heighted opening on the southwest corner of the building. These are some rendered views of the breakout spaces with their openable blinds, the main entrance, the courtyard from the lower and higher levels, and the external facade.
This section was divided into three phases. In the first phase, an extensive study was done in order to locate and classify the various zones that are present around the proposed site according to the demographic data. The entire site of Kharghar was analyzed to understand the surrounding context, the modes of transport for connectivity, the target residential areas, infrastructure, underdeveloped areas, upcoming facilities, and green spaces. There are various NMIMS campuses located in India which have been marked on the map along with the type of climate prevalent in these areas. Amongst these, we have attempted to narrow down on certain areas that have climatic conditions not too different from Navi Mumbai, which are Chennai, Dhule, and Shirpur. In doing so, we have identified the probable locations in which the axioms and fundamental module of our design could be implemented and replicated to create a building which may or may not resemble our building in form, but would in fact be an extension of the ideologies and reasoning behind our structure. In the second phase, modules of classrooms were created along with passages and oriented according to the climatic data in order to reduce the loads on the building as a whole. Iterations of the arrangements and placements of these modules were done, wherein experimentations were carried out with linear arrangements and volumetric arrays, as well as rotating individual modules in order to meet the spatial and climatic requirements. In the last phase, a suggested module of cinder block wall can be applied almost to all typologies, including multifamily and single-family housing, office and commercial complexes, and of course, educational buildings, depending on the type of plants that thrive in that context. These alternatives to green walls are much more sustainable, cost-effective, and easy to maintain.
Our first step to creating a social media presence to spread awareness online was through Instagram. A large number of like minded individuals watched and interacted with our content. Through 37 posts to date, we provided information about the contests of the competition and several methods to incorporate sustainable practices into one's project. A total of 13,168 impressions were received, with multiple reels crossing 3,500 views. And an additional step to spread awareness amongst the peers was through posters that we put up on our campus that provided information on net zero energy and water cycles, as well as passive design strategies that could be integrated into their next studio project. Thus, we achieved a cohesive, energy efficient building that provides students with a comprehensive and informed education. because ultimately net zero is a stepping stone to the journey of human evolution. Thank you.
Thank you.
Thank you, Team Venturis, and you finished well in time and delivered really well. Let's hear the jury's comments and take questions from them. Shriti, would you like to start?
Sure. Thank you. Thanks, Karma. Hi. Congratulations on that presentation. Um, I really like the way you have, described everything graphically, especially the modules. That was very comprehensive. My main feedback and question is around materials, because there are a lot of different materials used in your proposal, starting from agrocrete, AAC, corkboard, bamboo fins. Uh, I'm slightly confused. Where is agrocrete used and where is AAC used? Considering that this is Maharashtra, Kharghar, agrocrete has higher water absorption ratio, around 20%. So, what was your rationale behind picking agrocrete, besides, of course, being a more sustainable material in an area like that? And if you did, then why did you use both of them? Why did you just not went with one of the building materials, since both are non-load bearing elements in your structure? Second, you had mentioned a lot around downsizing your cost by improving or optimizing the steel in the building that is there in your multi-story building. So I just wanted to know, what is the per square meter steel that you sort of reached, which you felt was optimum and you were reducing uh, from the baseline? Like, was it around 4 to 5 kg per square meter? What was the range of steel that you finally came up with, which you think is optimized and helps in reducing the cost of the structure, because it's multi-story, so and most of the whole load is taken by the structural frame. So I would like to just know what that number or that calculation looks like. Uh, my third question would be that when you were talking about resilience, you mentioned PV were used as backup, but I didn't see anywhere in the layout any room for storage battery. So how are you, taking care of it, providing you? I'm so sorry for that. Providing backup. So, you know, mostly around materials and the backup that is not
Yeah.
visible to me.
Thank you so much, ma'am. Coming back to your first question about agrocrete, yes, like you rightly said, agrocrete has a high water absorption thing, and that is the sheer reason we did not use agrocrete for the whole building. We only stuck to using agrocrete in the internal spaces. The external framework that's there is AAC block, so that it's weather resistant and fits in the context. Secondly, about the grade of steel, this we spoke to our structural engineer. We wanted to decrease the overall floor to floor height also, so that we could incorporate services. Thus, there was one of the ways of doing it was to increase the steel, and actually by right sizing each and every element, so that you can detail out the internal spaces accordingly. So the structural engineer suggested that we use 4.5 as per square meter steel, which we use. Um, for the third question, that's about health and well-being. The storage of battery wasn't visible in any of the floor plans because it was in the basement. So we have allocated a room in the basement for storage of certain batteries, storage of extra electricity which is generated.
So just a follow up on that, since you're storing it in the basement, and
Yeah.
there'll be, like, there'll be more heat in that room, right? Because of the batteries.
Uh,
So how do you take care?
yes.
Like, are you providing anything for that? Any special?
Ventilation, normal ventilation which is provided in the basement. So we are adding fan coil units in the basement. So we provided two fan coil units instead of one in that particular room, taking care that it's an electric station room.
Okay, thank you.
Aarti, would you like to go next?
Uh, Thanks, Karima. Great presentation, team, and I guess, as you have yourself said, I think one of the teams which has followed the most iterative process of design, I must say. Couple of quick questions, specifically on the energy performance. So you're using a hybrid DRF system. It's basically going to provide chilled water, and you have these indoor units. I may be mistaken, but I did not see anything on the ventilation there. Have you provided some numbers as to what kind of ventilation you're going to achieve? Can you show it to me in the presentation?
Uh, yes,
Okay.
ma'am. So
Would you
you're
like to? Yeah.
yeah. So, ma'am, you're talking about the air changes per hour of the hybrid variable refrigerant flow system, right?
Yeah, air changes also. Yes.
Yeah, so we've taken 5 as the air changes per hour as per calculations, and we've inputted that data into design filter to see how the whole system works, and thus calculated our EPI accordingly.
And correct me if I'm wrong, what you're saying in the suggesting in the report at least is that you're going to use both natural ventilation and this hybrid VRF, right?
Natural ventilation and yes, hybrid VRF system.
So what time, what like how are you going to schedule it?
Uh, yes, so Mika, if you could go to those pie charts which we had initially. Yeah, slide number 4. So, ma'am, we've done this initial study wherein we had allocated and detailed out hours which will require external cooling and which won't require. So we are following this table for air conditioning and natural ventilation.
So just a couple of quick questions, and I think 3 or 4 questions. One is I think within these two charts, somewhere I have seen that there was a large number of cold hours, and you also mentioned that there will be cold and harsh winds in the winter. That seems a little out of place for Mumbai to have cold and comfortable hours in large numbers, in a large one of these two pie charts that you have at the right bottom right corner of the slide. So that's one observation. Secondly, these chilled water pipes, the pipes which are going to carry the chilled water from the VRF, the hybrid VRF system, are going to, it seems supposed to come from the rooftop. That's where you have placed the VRF system. But nowhere in your plan have you given any space, it seems, at least from the plans that I have looked at, there's any space for, I do not see a supply network. I do not see a supply network for vertical transmission, and I do not see a supply network of how you're going to distribute the chilled water to the classrooms and all other spaces. So that's something that I'm not clear how you're going to achieve it. Secondly, about the shading strategy, I agree. I mean, I really like what the way you are playing with the vertical elements, which is these fins, the bamboo fins. Although I'm not sure if the joinery details that you have provided are adequate or they will actually work out. But the question that I have is, if you go to slide number 30, and in this courtyard in the center of the school, it seems that the solar radiation ingress is more or less limited to the top 2 or 3 floors, the radiation, if I'm reading it correctly, March, May, July, September, and even less. So then why have all these vertical shading devices starting from level 1? When you don't, I don't think you need them there. Your courtyard is a very narrow space. uh, I doubt if you will need those, if I may say, very densely placed vertical fins within the courtyard. Uh, at the most, you may want probably, maybe horizontal shading devices at the lower levels or not at all. Because even if you go at the views that you have shared at the end of your presentation now, uh, the, yeah, so look at this courtyard. I mean, do you think that light or any solar radiation would really come into this space? And the same goes for the shading strategy for the external facade itself. It seems that it's uniform across all the facades, whichever direction they face. I would suggest that you look at it, not now, right now, but eventually you go back and look at it is these vertical fills the only strategy that you can use? Maybe you can cut costs and cut efforts and resources by looking for some other, you could use some horizontal shading instead of just relying on vertical shading across all the facades. Lastly, is your roof space adequate? Because you have a narrow roof profile because of the courtyard in the middle. So that leaves you, little space in terms of placing the PV array facing in the optimal direction. So have you calculated it? That's my question. I mean, have you looked at that aspect when you were designing the piece?
Yes, ma'am. So we have calculated the total consumption from the NREL website, and we had put in our roof area and the site area, and then the total energy requirement, and it was coming up to 32,000, which is almost 100,000 more than what we require. So
Okay, okay. Thank you. That's from my side. Thank you, Garima.
Thank you, Aarti. Over to you, Harsh.
Yeah, thank you very much. All right, just once again. So I think firstly, I felt that uh, after studying your report, I think the presentation was well organized, right? I thought the report was a little difficult to read, but your presentation was much clearer. Did more justice to all the effort you put in. Graphically, also, it's quite good. And I must comment that probably you're one of the teams that has done a lot of simulation work, right, of various kinds, and I think I would positively highlight that you've actually tried to play with those simulations, right, to understand different iterations, right, and I think that's a very positive sign going forward into your career as as architects and actually using sustainability tools, right. Now there are a couple of quick questions based on your report rather than your presentation. I think, what is your final cost of construction per square foot, if you can tell me? Because I think at some place I thought it was rather high, but what is it that you finally arrived at?
sir, the project cost is 90,445, which includes the land cost.
No, this is what, per square foot?
Per square meter, sir.
Per square meter. So you're saying about 9,000 rupees a square foot, but including land cost. So what
Including
what
land.
what what is it excluding the land cost, right? Because I'm not evaluating the land cost.
Yes, yes. So it might come up to 5,000 per square feet.
Right. Okay. So I think that's why we felt that it was
Yes,
slightly
yes.
on the higher side, considering that you have a relatively simple building, right?
Hmm.
So one of the things I thought architecturally that you could have simplified a lot of things, but since you went into kind of playing and kind of trying out many things, which is positive in its own way, but probably would have impacted a lot of the design decisions you eventually made. Um, there is a page which I think you had opened, page 30, which shows this line, in the courtyards, right? This temperatures. I think I'll go back again. I was quite curious. How did you arrive at this 27 degrees C inside? Like how did you kind of estimate that? Is it based on something, some simulation, or it's an estimation on some basis that outside is 2 degrees higher than your courtyard?
So essentially, sir, it was based on simulations. We aren't quite sure about the exact decrease in temperature, but that's what two or three softwares showed us. So that's why we put it out here. It's debatable.
Well, it's very interesting, something that you should kind of research further,
Yeah.
that kind of architectural forms have an impact on the temperatures contained in the air volumes between them, as well as the humidity of those contained volumes, right? That's why in a lot of kind of desert communities, courtyard is quite a popular form, right? It's okay you have not simulated, but something that other kind of simulations can predict. Okay, there was one thing that I noted in your report regarding water calculations. You have incorporated a fairly large amount of area, I saw in the reports, for collection of water on the vertical kind of surfaces that you have created. You have actually, instead of just assuming horizontal surfaces, which are side and kind of soft and hard surfaces, in your water calculation, you're assuming that there is certain water being collected on vertical surfaces as well. Um, why would you do that? And is there any thought? Well, why are you doing that? Basically, it's counterintuitive to me. I would not kind of use that for collection of water at all, right? Because you would have accounted for in the horizontal surfaces.
So we've taken it as like zero point 0.5, like a factor of zero point 0.5 for the vertical surfaces, like half of the area of the total vertical surfaces, which we would collect it, like it would kind of drain down to the horizontal level, and then that then would be collected and treated. Yeah.
Right, but you have already accounted for all the rain that falls by the horizontal surfaces, right? So that is actually what I understood from the report, is that that's actually counting it additional, right? And that's actually enhancing the amount of water that you're actually able to collect on site. That's
Yes,
what
sir.
I
So,
can read.
sir, essentially, it was based on a research paper which we read, wherein it said that if you see in section a building or a land, the amount of water that a land can capture can be depicted by a line. Wherein, if you see, if you just add a building on it, the perimeter of the building increases. Thus, the catchment also increases because.
But
Uh,
sure. Okay, sorry. Go ahead. Go ahead. Yeah.
no, no, sir.
Right. So, I mean, that is correct that you have more opportunities. If you have a tall building, maybe you have some opportunities to capture rain on various surfaces. But the total amount of rainfall on a piece of land, whether it's a tower sitting on top of it or a small building, spread out small buildings on it, would remain the same. But what I understood from your report is essentially you've used all your kind of horizontal surfaces and then added those vertical, right, as well
Yes.
onto it. So which I think is just overdoing the amount of water you're actually connecting. Have a look at it. That's what
Okay.
I understood from it. You can, I mean, the water amount of rainwater collected will fall down since those areas are quite large, right? That you've assumed,
Yeah.
and that will impact your calculations.
Yes.
Otherwise, I think very interesting, and I must encourage you for all the effort you've taken into using simulation tools. Well done on that. I think it's not easy to pick up these tools so easily and then use them kind of very freely as you're using them. But I think well done on that. Thank you.
Thank you, sir.
Thank you.
Thank you, jury panel, and thank you, Team Venturis.
Thank you.
So,
Thank
folks,
you.
that was our last presentation in the education division. Our esteemed jury panel has shown a dedication at assessing these entries. I want to thank the jury members for your thoughtful assessment and comments, and I want to congratulate all the finalists. As the jury coordinator of for this division, I have had the opportunity to see these teams submit their deliverables 1, 2, 3, and this final deliverable 4. They have done some incredible work. Let us not forget that these teams have discovered a way to collaborate and do integrated design while being physically away from each other during the last 8 months. I think that itself deserves a round of applause. This evening, the jury members will meet and decide the winner and runner up teams. Who will it be? Meanwhile, please make sure you have given your vote for the People's Choice Movie Award. And feel free to hang around and meet the jury members and other guests in the networking zone in the lobby. And you can see the work of all the teams in the divisions displayed in the project exhibit hall. You can access the hall in the main lobby. See you all tomorrow at 10 a.m. for another exciting day.